Okay, Jingsong, in 2 minutes we start. Okay, just a comment for some people were asking if they can ask questions via YouTube. You can write, but it's better if you want to ask questions to go to enter Zoom and ask questions, because we don't check all the time YouTube. But you can watch from the YouTube if you don't have any questions. Okay, so we're ready to start. So it's my pleasure to present the first speaker for today, is Professor He from Shenzhen University. And he will be talking about, I forgot your talk title. You can start whenever you are ready. Jingsong, can you hear me? Okay, блин. Все это время микрофон был выключен. Okay, I'm sorry, the microphone was switched off. So for those who didn't hear, if you want to ask questions, you can enter Zoom. If you have no questions, you can watch over the YouTube. So it's my pleasure to present the first speaker, is Jingsong He from Shenzhen University. So Jingsong, you can start whenever you're ready.
Okay, so can you hear me? So Sotis, can you hear?
We can hear you, yes.
Okay, thank you. So thank you, Sotis, to invite me to give a talk on this very important conference. So this, of course, this is my first time to give a talk on the Russia conference. So I'm very pleased to do this. So this the topic for this conference is about the integral system and the nonlinear dynamics. So my talk about the resonance between different waves like solitone, breather, and lamps. So this is my organization of my talk. So first of all, I would give you a very brief introduction about this background, and then we give you semi-rational solutions of the microsystem. So this semi-rational solution includes several solutions, for example, solitone, breather, lamp. So as we know, the breather is a combination of exponential function, but the lamp is a rational solution. So this semi-rational means this solution is a combination with solitone, breather, and other rational solutions. So the second part, I will give you a new solution, is partly reasonable solution between rational waves and breathers. So this means we can have several categories of solutions. So we just give you three categories, three kinds of solutions, and of course, in our paper, so we have more. So the last one, I will show you the fully original solutions between rational and breather. So this will show you some very hot topic about the logarithm. So this is what is the logarithm?
Jingsong, will you comment on this Macari system? We're not familiar with it. Will you show it?
What?
I think we're not familiar with Macari system. Will you comment on it?
Okay. Okay. So I will show you this one. I will show you this one, Macari system. Yes. I will show you this system. So now, here I will show you this one. I will show you, so later I will show you. So now we give you some background so about the linear waves because the audience of this conference are the experts of nonlinear waves. So I just mentioned some basic facts, for example, about the application of nonlinear waves. So this can be used in many places. So for both Einstein constellation, some financial system, and of course nonlinear optics and other fluid mechanics. So also we talk about something for the soliton, breather, and logarithm. So now today I will give you new results about two-dimensional case. So focus on this line logarithm. So I will show you what is the logarithm, what is the line logarithm. Okay, and we gave you the combination of these solutions at one formula. So this also the background. I will show you this. This is background for the logarithm. So in one-dimensional case, the logarithm is a special kind of rational solution, which is doubly organized. So this means localized in T, also localized in space. So the famous example of logarithm for the Archimedes breather, breather, if you do this limit, you can get the first order logarithm. Of course, you can have high order logarithms. This has been observed in water tank and in optical fibers. So now my question is, can we extend this localized solutions to higher dimensional case? So this means, so can we find the logarithms in two-dimensional case? For our examples, for example, can you find the logarithms in KP equation, in Davis-Sutherland equation, and others? So for today, I will show you this another new solution for the microsystem. I will show you what is the microsystem. So of course, we should looking for some potential application. So can we think about this logarithm is applicable in physics? Of course, this now for the one-dimensional case, this solution has been observed in fiber and in water tank. But for the two-dimensional case, no, there is no experimental observation. So we just do some theoretical calculation and figures. Okay, so today I want to show you some new patterns for this logarithm, which means how to get this logarithm. This means how to form this logarithm. So the physical mechanism is the soliton resonance. Okay, so now there are, of course, nonlinear wave resonant phenomenon. This research started from 1970s. The famous fluid mechanics professor Miles published his paper in JFM 1977 or 1977, two papers on JFM, introduced the resonance for nonlinear waves. Today, I will use this idea to try to find this resonant collision between lamps and soliton, and also for the breathers. In this process, I want to show you the lamps will split from breather and also can be absorbed, also fusing into the soliton. So this means this lamp can be just exists a very short period of time, not exist a long time. So this means this lamp is one kind of logarithm because it is localized around the evolution of time. Okay, so now I can introduce the microsystem. So you can say here, so microsystem is introduced by Macquarie, is an Italian professor. At that time, Macquarie is the student, is a PhD student of a very famous professor, Caragillo, so Francisco Caragillo. Now, so at that time, the Caragillo was interested in the multi-scale scalar expansion. So then he used this method, the multiple scalar expansion, find the new two-dimensional integral system. This one, you can say there are the coefficient, this one u, and there is a L1, L2 is a little bit longer, but the unknown function is u. So this equation, of course, is integrable, but the last pair is not very short. So I don't show you here. So you can find this paper in Journal of Mathematics, published in 1996. So now this paper, of course, this equation has been studied by many researchers. So also for me, so I want to use the Herta method to find this solution. So for this one, okay. So I skip the details. I just show you that this equation can be transformed to bilinear forms. So of course, this is the Herta method. So for you, if you use Herta method, you can find a very universal form of your solution for this U. Now we use this method. You can say here, find this one. So this is the solution you can find from, okay, I don't want this. I'll hide this. Okay, so now, so you use this double Herta method, we can find this solution. So this is a tau. This matrix you use determinant here, this tau n is a solution of this matrix system. So it's given by a rational form tau 1 over tau 0, and there is a way is this one. There is a derivative, the second order derivative with respect to y. Of course, if you look this form, you will think this is not very compact. It's tedious. So what's new compared with known solution? So in our paper, this is our paper, GMP 2003. So what's new compared with the known solution? So we have improved this matrix here, this elements. We insert, there is a constant this term, and we do the summation for here. So this is new. So for this, of course, this is you say it's simple, but this is a very effective, so efficient way to find a new solution. So by this improvement, so we get this solution. Of course, this can be verified by Herta method. So now, after we get this one, so we can give you some specific solutions. So sorry, I skip this one. If you are familiar with Herta method, you can follow my paper to get this solutions. So of course, after we get this tau function, so you can have following categories of solutions by choosing different parameters. So today I want to show you four interesting types for the partner resonant solution. So for this one, for n, we choose m means the rank of the matrix. So we consider n is 1. We use this n alpha. So n alpha is here, is for the this one, and also for this one. This means this situation. So okay. So now, so this means this n alpha determines the expansion, the order of your expansion, because there is a derivative. So you can say for this solution, there are two important factors. One is the rank of this determinant. Also, you can say the rank of this matrix. The second is the order of this derivative. So we consider, first of all, we consider n, the capital N, the rank of this matrix is 1, and this the derivative, the order of the derivative is 1 or 2. So then we consider n is larger than 1. So there are several combinations. So for this case, you can see here, n is 1. So n alpha, of course, 1 or 0. So second, we consider this is n, capital N is 1. This means the determinant is the dimension of determinant is 1. But the derivative is 2. And the last one is this, the determinant is 2, the rank of the determinant is 2, but the derivative is 0 or 1. So we also
Jing Song, sorry to interrupt. Could you please go back to the previous slide?
Okay.
Because it's the solutions are very difficult to read. You say in the very end of the slide that xi alpha are free parameters, however they satisfy particular equations. Could you please?
For this solution, this is tau function here. This is equation 2. There is u tau 1, tau 1, tau 0. Can you say this one? So if you substitute this one to not directly to the nonlinear microsystem, we go back to the Helmholtz form of this equation. So first of all, we should transform this equation to Helmholtz form. So then we verify this solution is indeed the solution of Helmholtz form. So this is the method to looking for solution by Helmholtz method. That's okay?
Yeah, okay.
Okay, so I have to speed up. So because the time is 20 minutes. Okay. Now the following is more simple because I just show you some figures and do a very short explanation. So now we want to show you this partly resonant condition for the first case. You can see here. So we choose this n is 1, and this is the order of derivative in our determinant. So is 1 or 0. Now you do a very simple, but not very simple. So you can do this by maple. You can get this solution. So this one. So now this solution you can say not very tedious, but it's still not easy. So now this can be verified directly substitute this into a microsystem. We have done this. So now for this formula, we will think about. So this is the collision of lamp and the breather. So I will show you these figures here. So you can see here, this is a breather. So it's a periodic lamps, and this also here is a lamp. Now this lamp, so we can say this is a resonance. So you can say this lamp will disappear. So maybe it's absorbed. It's facing from split from this one. So you can see here. Now this figure show you we have calculated this direction of this breather and this solution of rational solution for this one. Now we also can find the maximum and minimum value for because breather and a lamp have 3 collision points. So we find this one. Now for this, of course, this has calculated in my paper. So for this talk, we don't go into details. So you can see here, for this one, there is a new lamp appeared. This means this is split from this breather. So also this, the second law to verify, so what the trend of your amplitude. So you can say here, this is the maximum and the minimum, maximum and minimum. So indeed, so this is appeared. It also can split from this one. So this now if you choose, so here. So if you choose the special case for above this one, so if this one, the P1, P2 is a paired complex conjugation. You can see here, P1 is I plus 1, P2 is I minus 1. This is a complex conjugation. For this case, so of course this is not 0. The real part, imaginary part is not 0. Then you can get a lamp and a line breather. So what's in the line breather? Line breather you can say is a periodic solution on this whole XY plane. So you can say this here. this background, this is the periodic. So now then you can say there is a lamp. So at last you can say these are two peaks. Then the T is very large, it disappeared. So this means there is a lamp fusing so into your background. Into the background is a lion prism, is a periodical structure on whole XY plane. So I always use this observation, this paired complex conjugation, to construct this line blizzard on whole XY plane. So then there is the lamp will appear, then disappeared. So is in a short period of time. So this is the first kind type of this solution. The second, I will show you very fast. Okay, so it's two lamp. So we take the determinant as the rank is n, but we consider a little bit higher order derivative. Then you still can find this semi-rational solution. Also, you can do a little bit analysis. You can find the trajectory of your breathers and your lamps. So now you can see here. This is a lamp one, lamp two. This is a breather. So you can say this one. Now this you can say at last there is a breather. So this means this two lamps so facing into the breather. So you can say absorbed by this breather. So this why this happened because there is a resonance between this lamp and the breather. So now also you can use the paired complexity.
Could you please clarify what is a semi-rational solution in terms of the function? What does it look like as a function, a semi-rational?
Here, semi-rational solution is this one. You can say this one. For this solution, this must be semi-rational because this tau 1 over tau 2. So for the tau 1 is a polynomial. Tau 0 is also polynomial, but this one combined with exponential. So if rational solution means polynomial over polynomial, but for this case, the polynomial multiplied by exponential function. So this means semi-rational. So it's clear for you? So my answer is okay.
Sorry, the microphone was switched off. Yes, okay, yeah, thank you.
Okay, thank you. Now, so at last we can get the rational solution. So this is, now we consider this two breather. So we have two, last I will show you this one. Also, you can choose this paired. For the paired solution, you can get two lamps and two lamp breather. So what's this one? Yes, here, the background is periodic. So we think this is named by line breather because this is a breather. If you do this direction, periodic. So there are lamps. You can say this is the lamps and this is the lamps. So there are two lamps. You can find this for this situation. Also, this figure to verify this observation, you can say this maximum now is the same as this background. This means this solution is disappeared, but you can say going back to this background. So this one is appeared. Also, you can say it's created from this background. So now I want to show you the last one for this. Okay, so for higher, so we can skip this one. Now I want to show you this. Okay, for this case, so we have a higher order for n is larger than 2. So we have 6 kinds of dynamic evolution. So I will show you this one, the 2 lamps and the 2 breathers. You can see here. This one, there are 2 lamps. This is the 2 breathers. There is a lamp. So now this is breather 1, breather 2. Now this one is just exists very short period of time, and this one is created. You can say separated from this breather. So I maybe my time is okay. I just show you last one for the Fourier resolution for this case. So now I'll show you the last one, the Fourier resonant condition. If you consider this one, you choose this parameter, now you can get the new solution is line segment and logarithm. So this is the resonant solution of the breather and the rational soliton wave, the line loop and the lamp. Now I'll show you this one. For this case, you can find the trajectory for these two breathers. For these two breathers, now there is a line loop. So line loop it means is a line on whole xy plane. So but for this case, due to the resonance, you can say this is a line segment. But this line segment just exists a very short period of time. So this why we call this is line segment logarithm. So this means line segment logarithm. Because this line segment just exists very short period of time and also localized on xy plane. You can see here this line segment disappeared. This is we can say the density plot to verify this observation. And also you choose this one, you can have the interaction between breather and lamp. So we do a little bit of analysis. You get this maximum and minimum, and you also can find this. Now for this case, this is a maximum and minimum to verify this lamp. You can say this is a two breather. Here now there is a lamp appeared, but this lamp just can exist a very short period of time, then this lamp disappeared. So we say this lamp is log lamp, means just exists very short period of time. Okay, so due to the time limit, I just give you a very quick presentation about our new solutions. For the resonance, we in my group have done almost several papers published in these journals. So the co-authors, this Ji Guanglao and usually my students, this is Professor Boris Bogas and Zhou from Shanghai University, this is the India professor, this is the Romanian professor. Okay, so thank you very much for your attendance and comments.
Okay, thanks very much. Are there any questions or remarks? Okay, there's one question.
Thank you very much. It is Victor Buchstaber. Thank you very much for your talk. It was very interesting for me. And my question is such. In our seminar, in this area work Piotr Grinevich. Did you know his result, his approach? Because I certainly informed him about your result. And I think it will be very interesting to compare his approach and your approach in this very exciting area.
With Paolo Sartini, is that a paper?
Yes, he has worked with Santini, but he's talking about Grinevich.
Okay, thank you, yes.
Okay, thank you.
Thank you.
Any more questions or remarks? Can I ask, what about these Macquarie systems? What do you know in terms of integrability? Lax pairs, Darboux transformations?
Yes, this has been done. Lax pair has been given by Macquarie. So at 1996, the Darboux has been done by others.
What about the solutions you showed, the semi-rational? How are they constructed? Are they constructed via the Backlund transformations or what?
It's different. For the Backlund transformation, I think it just gave the soliton solution. For our solution, so we are it's more complicated, it's more universal because we can get soliton, also can get breather, and also can get rational solution. For the Backlund transformation, usually you can produce soliton solution. So I know some people have done Backlund transformation for this model.
And can I ask a final question? So there are other generalizations of the nonlinear LLS equation, higher dimensional. Is there any, I don't know, known? How is Macquarie system compared to other multidimensional versions of the NLS equation?
So you mean you want to compare?
Okay, I see you've written on your slide that is comparable to
Yes.
David Stewart's on the question.
Yes. So from my opinion, from my experience to construct this solution, so all of this can have a soliton breather and the reasons, but the diverse solid question is very, I can say, exceptional, because only for this diverse solid question we have found the rational logarithm. For others, include PP, other solution, two-dimensional cases, we didn't find rational logarithm. We just found semi-rational logarithm. So this is the difference I found before. Maybe you can find others in the future. Okay.
Yeah, okay, thanks very much, and thanks very much for a nice talk.
For your organization.
So, let's thank the speaker again. So it's my pleasure to present the second speaker for today's Dmitry Talalayev from Moscow State University. And he will be talking about multi-valued quantals and associated bialgebras.
Thank you very much. I will talk in Russian. I have slides in English. И прежде всего я хочу поблагодарить организаторов конференции за возможность выступить здесь и пожелать этой конференции в будущем укреплять связи между двумя замечательными направлениями современной математики. Это задачами нелинейной динамики и интегрируемыми системами. Мой доклад частично направлен на эту задачу.
Извините, а слайды будут показывать? Потому что в Zoom нет слайдов.
Okay, that was my mistake. 1 second.
В докладе пойдет речь о некоторых результатах, полученных совместно с Валерием Георгиевичем Бардаковым, Виктором Матвеевичем Бухштабером и Татьяной Анатольевной Козловской. И прежде всего расскажу о происхождении понятия многозначной группы, которая возникла в 1971 году в контексте задач алгебраической топологии в работах Бухштабера и Новикова, далее было развито в работах Бухштабера и Риса и многих других авторов. Само понятие многозначной группы связано с теорией инвариантов, с характерами Фробениуса, симметрическими функциями и имеет огромное количество приложений, в том числе, например, в геометрии симметрических степеней, в доказательстве аналога теоремы Колмогорова-Гефанда, о которой я скажу чуть позже. Этот сюжет относится к нынешней конференции, потому что имеет непосредственное отношение к дискретным динамическим системам, из которых я бы упомянул задачу у тройках Маркова, соответствие Эйлера-Шаля и топограф Конвея. Нет возможности говорить подробнее об этих замечательных сюжетах, но именно присутствие структуры действия многозначной группы в этих задачах позволяет описывать стохастические свойства этих динамических систем. В названии фигурирует понятие квандл, и это одна из алгебраических структур, которая возникла в маломерной топологии, в теории узлов, но интенсивно используется в теории интегрируемых систем. С этой структурой связаны многие решения уравнения Янга-Бакстера. И в топологии уже возникали многозначные версии понятия квандла. В этом докладе я введу такое понятие и прокомментирую некоторые алгебраические структуры, которые с ним связаны. Вот. А ближайшей целью нашего исследования является построение теории представлений квандлов и многозначных квандлов, которая может позволить строить новые инварианты в топологии, а также новые дискретные интегрируемые системы. Я начну с определения многозначной группы. Это множество с бинарной операцией, но которое принимает значение не в множестве x, а в мультимножествах, в элементах симметрической степени x. Вот так обозначается эта операция. И под ассоциативностью уже понимается совпадение двух n квадрат мультимножеств. Потому что два раза применяя эту операцию, мы получаем n квадрат мультимножества, и требуется, чтобы эти мультимножества совпадали без отождествления экземпляров. Единица. Единица – это элемент, и требуется, чтобы умножение на этот элемент было диагональю. То есть это было мультимножество, состоящее только из элементов x, на который здесь умножается. Обратный элемент – это отображение множества x в себя такое, что произведение в этой многозначной группе обратного элемента на x содержит единицу. Это не обязательно диагональ от единицы, но вот в этом мультимножестве единица должна содержаться. Вот. Ну и, собственно, n-значной группой называется множество с операцией, которая удовлетворяет этим свойствам. Имеется такая каноническая процедура построения многозначных групп, которая называется косет-конструкция, и она строится по дополнительным данным. Рассмотрим обычную группу и некоторую подгруппу автоморфизмов этой группы, порядка n. Тогда на множестве орбит группа А по действию подгруппы автоморфизмов этой группы возникает структура многозначной группы вот с такой операцией умножения. Мы должны для двух классов этого множества классов перемножить все представители и взять классы, в которых они находятся. Вот. Оказывается, что это будет мультимножество, и все аксиомы многозначной группы при этом удовлетворяются. Я приведу архетипический пример такой конструкции. Это группа, которая носит имя Бухштабера и Новикова. Она получается, если для абелевой группы целых чисел рассмотреть два таких автоморфизма, тождественный и обращение знака. Множество орбит такого действия – это неотрицательные числа. Операция задается вот таким образом. Оказывается, что уже такой пример является содержательным и возникает во многих приложениях. Вот значит, такой пример многозначной группы. Мне нужно понятие n-гомоморфизма. Оно немножечко технически осложнено, но давайте попробуем пройти. Значит, я стартую с пары алгебры А и коммутативной алгебры Б. Я рассматриваю все такие линейные отображения из А в Б, которые называются следовыми отображениями, или, ну, в общем, вот, которые удовлетворяют такому условию, что они на коммутатор спускаются тривиально. И дальше по каждому такому следовому линейному отображению я буду строить семейство таких производных К полилинейных автоморфизмов из тензорных степеней А в Б. Они строятся рекуррентно. Первый просто совпадает с самим F, второй производный гомоморфизм строится вот по этой формуле. И дальше есть общая рекуррентная формула для производных таких линейных гомоморфизмов. Вот такой гомоморфизм называется n-фробениусовым гомоморфизмом, если выполняется два условия. То есть если на единице значение n, а n плюс первый производный гомоморфизм равен нулю. Давайте убедимся в том, что один фробениусовый гомоморфизм – это просто гомоморфизм. Это то, что называется там, кольцевые гомоморфизмы. Значит, ну вот, нужно потребовать, чтобы на единице принималось значение 1, а φ2 равнялось нулю. Но это и означает условие того, что это кольцевой гомоморфизм. Гомоморфизм алгебры А в алгебру Б. Я приведу классическое утверждение, играющее огромную роль в современной алгебраической геометрии, ну, в общем, вообще в том, насколько алгебра с геометрией связаны. Это теорема. Я думаю, что близкие утверждения возникали и в других контекстах, вот, но абсолютно точно в таком виде она была сформулирована Колмогоровым и Гельфандом. Значит, рассмотрим компактное Хаусдорф-топологическое пространство и отображение вычисления, которое по точке пространства строит линейный гоморфизм из кольца непрерывных функций на x в поле комплексных чисел. Вот такое отображение. Теорема утверждает следующее, что это отображение – это гомеоморфизм на множество кольцевых гомоморфизмов. То есть кольцевые гомоморфизмы – это точки, кольцевые гомоморфизмы из кольца функций, непрерывных функций – это точки самого пространства. У этого утверждения есть замечательный недавний аналог для симметрических степеней топологического пространства X. Рассмотрим пространство X и его симметрическую степень. Это просто фактор множества по действию симметрической группы. И будем рассматривать аналог отображения вычисления из симметрической степени в линейное пространство гомоморфизмов из кольца функций на x в поле комплексных чисел. Это отображение строится как сумма во всех, ну вот, по всем элементам этой симметрической степени. Это неупорядоченная сумма, то есть корректно определена на вот этом множестве. Теорема Букштабера и Риса утверждает, что это отображение вычисления, nт степень. В общем, n версия отображения вычисления – это взаимно однозначное соответствие с симметрической степени x и n гомоморфизмов Фробениуса из кольца непрерывных функций на x в поле комплексных чисел. Некоторые из этих свойств я хочу перенести в категорию квандлов. И для этого я напомню, что это такое. Квандл – это множество Q с бинарной операцией, но которые немножечко отличаются от групп. Например, x на x – это всегда x. Для любых x и y существует единственный z, такой, что z умноженный на y равен x. И третья аксиома – это вот такое условие согласованности операции. Ну, полезно считать это аналогом ассоциативности в группе, но вот я сейчас объясню, почему. Вот алгебраическая система с таким набором аксиом называется квандлом. Если опустить аксиому Q1, то эта система называется REC. Основной пример этой структуры, который надо держать в области внимания, это так называемый присоединенный квандл для группы. Значит, если у нас G это группа, то можно на этой группе ввести операцию звездочка, которая есть сопряжение А с помощью элемента B. Вот оказывается, вот эта операция звездочка удовлетворяет данным аксиомам. Вот. Ну и исторически именно в этом контексте возникло понятие квандла или самодистрибутивного группоида при описании фундаментальной группы дополнения к узлу. Вот соотношение Вертингера в этой группе – это только соотношение сопряжения, поэтому оказывается достаточно рассматривать квандл, а не фундаментальную группу. Есть еще несколько примеров, но поля этой книги слишком узки. N значный рек – это теперь множество с двумя операциями, звездочка и сопряженная звездочка. Эти операции отображают теперь и та, и другая в мультимножество. И мы требуем несколько аксиом. Значит, обратимость – это следующее, что вот такое мультимножество – это аналог второй аксиомы. Это множество, вот эти два множества совпадают, не совпадают, содержат элемент x. И самодистрибутивность теперь более, ну, в общем, вот к такому мы определению пришли, оно эффективно в тех задачах, которые мы сейчас умеем решать. Если вы помните, самодистрибутивность – это равенство уже неоднородное. Здесь 2 операции, здесь 3 операции. Поэтому если мы будем перемножать, применять эти операции, то здесь получится n квадрат мультимножества, а здесь n куб мультимножества. В общем, в нашем определении требуется, чтобы вот это мультимножество было подмножеством вот этого мультимножества. Да. Значит, это было определение многозначного врека. Для определения многозначного квандла требуется еще вот это условие, чтобы x содержалось в произведении x на x. Для многозначных квандлов выполняется аналогичная общая конструкция, косет-конструкция, которая звучит примерно так же. Значит, если у нас есть квандл, есть некоторая подгруппа в группе автоморфизмов квандла порядка n, то на множестве орбит существует структура многозначного квандла. Значит, и вот так звучит эта теорема. Пример многозначного квандла. Самый простой – это если взять группу S3, симметрическую группу на 3 элементов, и взять подгруппу S2, ну, внутренних автоморфизмов вот этого квандла S3, вот, то множество орбит будет состоять из 4 элементов, и на этих 4 элементах есть вот такая таблица умножения мультиквандла. Ну, самый интересный элемент вот здесь, вот эти элементы, потому что они не диагональные. Вот, и это, на наш взгляд, иллюстрация того, что это нетривиальная конструкция многозначных квандлов. Еще один пример, ну, он тоже иллюстрирует то, что бывают не диагональные многозначные умножения в квандлах. Вот, но я хочу пройти дальше. Вот, и связать понятие n-гомоморфизма с многозначными квандлами. Я напомню сначала утверждение про групповую алгебру многозначной группы. Вот пусть есть многозначная группа, и на ней задана такая операция, тогда групповая алгебра может быть определена с помощью такого умножения. И групповая алгебра является еще, она оснащена еще и коумножением, естественным коумножением, вот таким. Сейчас, простите. Значит, я тут рассмотрел еще алгебру функций, двойственное пространство к этому пространству. Вот на алгебре функций есть уже обычное коммутативное умножение, и вот на этом пространстве я ввожу теперь коумножение по такой формуле. Но это двойственное коумножение к вот этому умножению. В общем, групповая алгебра в многозначной группе имеет умножение ассоциативное, оно еще будет и коммутативным, и есть коумножение, которое коассоциативно, но уже не кокоммутативно. И я здесь не привел утверждение. В общем, этот объект является так называемой n-хопфовой алгеброй. Здесь умножение и коумножение связаны не как в хопфовых алгебрах, а так, что коумножение является n-гомоморфизмом умножения. Я введу понятие биалгебры, которое теперь связано сначала с рэком, а потом с многозначным рэком. Можно делать то же самое. Можно рассматривать Значит, это рековая биалгебра, река Q. Это пространство, векторное пространство, порожденное множеством Q. На генераторах этого векторного пространства, на базисных элементах вводится умножение, оно дальше по линейности распространяется на все векторное пространство, и вводится стандартное ко-умножение. В силу того, что на квандле операция самодистрибутивная, а не ассоциативная, условие согласованности выглядит немножечко иначе. Вот это условие, которое вот в этих линеаризованных терминах означает самодистрибутивность квантла. Вот. Это просто то, что коумножение – это гомоморфизм коалгебр. Да. Я хочу ввести двойственное пространство. Ну, это пространство функций на квантле. Вот на нем тоже вводятся две операции. Это обычное поточечное умножение, оно ассоциативное и коммутативное, а коумножение связано с умножением на рейки. Вот в терминах этих двойственных операций все условия согласованности записаны этими двумя формулами. Значит, это это условие согласованности, а самодистрибутивность записывается с помощью такого условия в терминах операций на двойственной алгебре. И будем называть линейное пространство корековой биалгеброй, если оно оснащено вот этими двумя операциями, умножение ассоциативно, и выполняются вот эти два условия согласованности, одно из которых означает, что коумножение – это гомоморфизм алгебр, а второе, в общем, кодирует условия самодистрибутивности на квантле. Значит, n-корековой биалгеброй называется то же самое, что корековая биалгебра, но теперь мы требуем, чтобы коумножение было n-гомоморфизмом умножения. И основная теорема состоит в том, что если Q – это n значный рек, то алгебра функций на нем – это n-корековая биалгебра. Я скажу буквально о нескольких приложениях, которые уже фигурировали в топологии. Тураев рассматривал мультиквандлы, которые ассоциируются с парой линейно связанных топологических пространств. Это очень похоже на упорядоченную версию нашего определения n-значного река. И в отличие от теории n-значных групп, упорядоченные n-значные реки – это очень содержательная часть теории. Есть много примеров, вот в том числе они фигурируют в топологии. Еще один пример, тоже приходящий с топологии, связан с понятием виртуальных узлов и виртуальных кос. В том числе Кауфман разрабатывает теорию виртуальных кос с несколькими виртуальными операциями. Как я уже говорил, наш интерес во многом связан с развитием теории представлений квандлов. И вот эта идея рассматривать квандловые алгебры и их свойства, но она мотивирована ролью групповой алгебры в теории представлений групп. Это связано с теоремой Берцайнда, с классификацией конечномерных представлений групп. Спасибо большое за внимание.
Спасибо большое. Вопрос или замечание?
Еще пока нет. Антон хочет задать.
Антон, вопрос, да? Давай.
Меня слышно. Я вот хотел спросить, а вот может ли быть применением построения инварианта заузленных графов Потому что там может быть вершина большой валентности, и нету канонического порядка на ребрах этого графа.
Да, это очень хороший вопрос, скорее всего, может.
Мгм. Да, здорово, потому что там как раз один инвариант, он строится из условий, что там что-то, инвариант относительно всех перестановок, а тут такого не надо делать, или там вращений. Это, наверное, может быть применимо.
Да, Антон, вы правы, это очень важное перспективное направление.
Извините.
Дима, спасибо очень большое за доклад. Я просто хотел сделать несколько комментариев. Первый, я первый раз их увидел, и меня немножко вздрогнул, потому что есть два математика, которые пишутся по-разному, а произносятся одинаково. РИС и РИИС. Вот в теории квантовых групп пишут, вот как ты пишешь, РИС. А мой соавтор RI2И, Вот. И это надо иметь в виду, потому что это в самом деле, вот мой коллега Элмор Рис, к сожалению, недавно умер, это один из выдающихся математиков. Он начал со знаменитой работы, наверное, вы слышали, это работа Майкла Ти и Элмор Рис по уравнениях, не уравнениях, а расслоениях на кривых. Это вот та знаменитая теорема. Ну вот, а потом, короче говоря, меня с ним очень тесно связала эта тема. Мы много работали, но прошу вот писать РРС. Это первое. Второе. Вот когда вы упомянули теорему Колмогорова-Гельфанда, Буштабра-Риса, я хочу обратить внимание, что вообще вот эта деятельность на современном уровне тесно связана с теорией квантовых групп. Вот если после Дринфельда все прекрасно понимали, что надо изучать не только кольцо функций, но и двойственное кольцо. А восходя к классическим работам, теорема Гильберта о нулях, теорема Гельфанда Колмогорова говорила, что надо рассматривать пространство непрерывных отображений кольца функций, функционалы. И вот теорема Гельфанда и Колмогорова показала, что вот в этом громадном пространстве лежит само пространство X как множество точек, правильно? И дальше возникла проблема. Множество точек – это же функтор, когда в X отображается в Y, то и так далее. И проблема, которая до сих пор всех волнует, такая. А какие еще функторы пространства X лежат в громадном функциональном пространстве? И вот наш результат, что там заведомо лежат симметрические степени, это связано со многими задачами алгебраической геометрии и так далее. Просто я обращаю внимание, что это как раз прямой выход. Я потом в свое время построил, как вы знаете, квантовую группу в кабардизмах и так далее. Все опиралось на то, что вот теория n-гомоморфизмов нас сразу выводит в теорию квантовых групп. Спасибо.
Дима, у меня тоже вопрос.
Извините, пожалуйста,
Да.
Сирис, можно я задам вопрос?
Конечно.
Я просто тут читаю, что предполагается использовать теорию для обсуждения, называется, виртуальных узлов. Я просто думаю, что означает, что есть пример мультиквандла, связанного с узлами. Вот пример квандла, связанного с узлами обыкновенными, Дима приводил во время доклада. Можно ли также быстро описать пример мультиквандла, связанного с виртуальным узлом?
Быстро не могу, может, это направление для
То есть пока
дальнейшей деятельности.
Нет, я просто думал, что я хочу понять, собственно, как это выглядит. Все, извините, нет. А какой-то другой пример вот есть, который вот является мотивирующим?
Вот у Тураева есть мультиквандл. Вот то, что в первом пункте отражено.
Да. Ладно, спасибо.
Дима, один последний вопрос, что вот это условие, которое почти ассоциативность, я думаю, что называется автодистрибутивность.
Самодистрибутивность.
Да. То есть ты даже сам показал мне когда-то, что как красиво есть интерпретация, как трехмерно совместимое отображение. И там для multi-valued RAC есть такая-то интерпретация?
Я думаю, что да. То есть просто само отображение будет многозначным.
Да.
Но это тоже раскраска вот этих комбинаторных структур, которые возникают при построении уравнений n-симплексов. Я уверен в этом.
Хорошо, спасибо. Есть другие вопросы или замечания? Тогда еще раз спасибо за интересный доклад. И следующий докладчик, это онлайн, это Сергей Агапов. Сергей, вы с вами?
Yes, I'm here. Can you hear me?
Yeah, one second. Yes, I can hear you very well. Just let me stop sharing here so that you can share your slides.
Yes, just a minute.
Perfect. We can see everything.
Is this okay?
Yeah. So, okay, Sergey, you can start whenever you are ready.
Такой вопрос. Скажите, пожалуйста, мне лучше на русском говорить или на английском?
Ну, решайте сами. Есть только один участник, который не говорит по-русски, я насколько я вижу.
So maybe I will speak English. Yes, then, yes. So I may start, right?
Yes, please, you can start.
Okay. So first of all, I want to thank the organizers of this nice conference for possibility to participate and give a talk here. And I will be talking about integrable Hamiltonian systems, which describe magnetic geodesic flows on two-dimensional surfaces. And the main results were obtained in this series of papers, which were written together with Mikhail Bialy, Andrei Evgenich Mironov, Alexander Volozhenich, Alexey Potashnikov, and Vladislav Shubin. So, briefly speaking, in the first and in the third papers, we construct new integrable examples of magnetic geodesic flows on two-dimensional surfaces at a fixed energy level. In the first paper, this is the two-dimensional torus, and the third paper, the configurational space is not compact. It's either a cylinder or plane. And in the second paper, we obtained some results concerning integrability at several different energy levels simultaneously for magnetic geodesic flows. So let me start, and since the main object is magnetic flows which are given by magnetic Poisson bracket, so let me briefly recall what is Poisson bracket and its relation to Hamiltonian systems. So if you consider manifold M with local coordinates, then the Poisson bracket is just a map which acts on a space of functions, smooth functions defined on this manifold, and as a result we have one more function. It's a bilinear schizometric form which satisfies, as we know, Leibniz rule and Jacobian identity. And in local coordinates it is given by the following way, where Hij is a tensor with two upper indexes. So having the Poisson bracket, we may define the Hamiltonian system in the following standard way. And during the talk, I will be considering the very typical case when our manifold is a cotangent bundle of a certain manifold n of dimension n. So this is very typical in mechanics. And as we know, due to Darboux theorem, there exist canonical coordinates, special coordinates x1, xn are coordinates on the base, on n, and p1, pn are conjugate momenta. And in these coordinates, the Poisson bracket is of the following form, and so can you see my Hamiltonian system?
Yes.
So in these coordinates, the Hamiltonian system takes the canonical form as it is written here in this line. So let me recall what is geodesic flow. Suppose that there is a Riemannian metric on the surface, and the geodesic flow is given of this metric is given by the following Hamiltonian system, where H is the Hamiltonian. This is the inverse metric tensor, and very important notion here is the one of first integral. This is just an arbitrary function which is defined on the tangent bundle. This is the function of coordinate and momenta, such that it conserves along the trajectories of the system. So it means that the Poisson bracket of F and Hamiltonian vanishes identically. So if these two functions, F and H, are functionally independent almost everywhere, then this Hamiltonian system is completely integrable in the sense of Liouville, and in this case, it is possible to integrate the equations of motion in quadratures. Okay, so the standard classical problem in differential geometry is to say for a given manifold, for a given surface, to describe all the Riemannian metrics with integrable geodesic flow. Okay, now let me go to magnetic Poisson bracket, which is given by the following way. As you can see, momenta no more commute. In this case, omega ij appears here, and it corresponds to a non-zero magnetic field. So magnetic Hamiltonian systems can be given in the following way, and throughout this talk, I'll be considering the magnetic geodesic flows on two-dimensional surfaces. So this system. Equivalent way to add the magnetic field is to say that in addition to the standard symplectic structure, we add the following closed-to form. So the magnetic Poisson bracket in these coordinates takes such a form. And in this case, the problem is follows: to describe all the pairs of Riemannian metrics and magnetic fields such that its geodesic flow is integrable. So let me recall some very well-known integrable cases. First of all, without magnetic field. These are two classical cases. In the first one, metric doesn't depend on one coordinate. X is a cyclic coordinate, and the corresponding momenta conserves. In this case, it is linear in momenta. The first integral is linear in momenta. Second case corresponds to Liouville metrics. Coordinates are separated here. Lambda 1 and lambda 2 are two arbitrary functions, and in this case, there exists a quadratic in momenta first integral. So these examples happen to live on the two torus, for instance. So they are not necessarily local; they might be global. And in contrast with these two examples, we consider this problem in the presence of a magnetic field, and two more examples are given here. The first one corresponds to the Euclidean metric and the constant non-zero magnetic field. And in this case, there also exists a linear first integral, but it is already non-homogeneous in momenta. And if we want to live on the two torus, for instance, then we may consider an arbitrary periodic function, say cosines of this function, to be periodic. So actually, this is the simple exercise for students to check, to verify that the trajectories of, in this case, are just Larmor circles on the plane. So this is very well known. And the second example is as follows. Here we can see that the metric and magnetic field does not depend on x, and so the corresponding momenta conserves, but this integral is already not homogeneous as well. And these two examples are the only known examples of integrability of magnetic geodesic flow at all energy levels simultaneously, as far as we know. So what I would like to say here, I'd like to point out that there are two different problems. The first one is about integrability at all energy levels simultaneously, and the second one is about integrability at least at a fixed energy level. And if we consider the standard geodesic flow without magnetic field, then we all know that these two problems are equivalent in the following sense. From the geometrical point of view, the trajectories will be just the same, and only up to parametrization. So increasing the energy, we increase the Hamiltonian, increase the momenta, and so it's just a different velocity. But trajectories will be the same up to the reparametrization. But this is no more true in case of magnetic geodesic flows. The dynamics on different energy levels is different, it's just different. So in case of the presence of non-zero magnetic field, these two problems have to be studied separately. Okay, let me go further, and let me briefly explain the technique, how to study integrability at a fixed energy level. So we may fix Hamiltonian to be C over 2, where C is a constant, and at this energy level, we may introduce one more coordinate, phi, and this is the parameterization of momenta on this level surface. So we have to write down the equations of motion at the following at this energy level, and this can be done in the following way. And we obtain that an arbitrary function f on x, y, and phi at this energy level must satisfy the following identity to be the first integral. So this condition has the following form. So it is just the left-hand side. It is just a polynomial in exponents, and the form of these coefficients n, k depends on the form of the first integral f. For instance, if f is the first integral which is polynomial in momenta or maybe rational in momenta, then these coefficients n, k will also be polynomial, either polynomial or rational in momenta. And what is interesting that in this case, the left-hand side also has a polynomial form in respect to c, to the constant fixed energy level. And this is a very simple moment, but it helps to prove, for instance, the following theorem.
What about the integrability of this? Can you go one slide back, please? So you say, so do I understand correctly that all the solutions of these partial differential equations for f are first integrals of the system, dynamical system you wrote, the Hamiltonian equations, yeah?
Sorry, could you please repeat the question?
Okay, so there's a question. So do I understand correctly that all the solutions of these partial differential equations for f capital are first integrals of the Hamiltonian equations, the system you wrote just before that, yeah?
This is the partial integral. So this is an integral only at the fixed energy level, h is equal to c over 2.
Okay, when you fix the energy, I see.
Yes, yes.
Okay, yes. Sorry, thank you.
So it is very natural since the dynamics at different energy levels is just different. So in case of magnetic flows, it is natural to consider integrability only at a fixed energy level.
Yeah, I understand now, thank you.
Here I would like to describe one result which concerns polynomial integrability at different energy levels. So suppose that the magnetic geodesic flow into surface admits a polynomial in moment of first integral f, which is of an arbitrary degree n, and we assume that f conserves simultaneously at n plus 1 over 2 or maybe n plus 2 over 2 pairwise distinct energy levels. So it conserves at a finite number of energy levels. Then it necessarily states that f is the first integral at all energy levels simultaneously. So this is due to the previous slide that I have already explained. So the left-hand side here is just polynomial in C, and we know that it may have at least no more than n roots. So as soon as we assume that f is the first integral at many enough number of energy levels, so it necessarily means that all the coefficients must vanish, and this is equivalent to integrability at all energy levels. So this is the simple result. And so let me go to integrability only at a fixed energy level. And in this case, there exist many integrable cases. The first one is about quadratic first integrals on the two torus at a fixed energy level. As it was shown by Bialy and Mironov, this problem can be reduced to the following quasi-linear system of PDEs. Here, this is the column of unknown functions which depend on x and y, and so lambda is a metric, and these coefficients, the first integral, the coefficients of the first integral are expressed in terms of these three unknown functions. So we obtain such system, and here exist many smooth or even analytical solutions to the system. The first one can be extracted from the construction which was obtained by Daritze, Grammatikos, Romani, and Winternitz in 1985. So I won't go into details, but just briefly describe the solution. Here E is just constant, and S and R are two elliptic functions. So this construction is parameterized by a finite number of constants, and they have to be chosen such that there are smooth periodic solutions, and they happen to live on the two torus. So this is the only known non-trivial solution of this problem, which can be written down explicitly. And it turns out that there are many other solutions. So this is our result together with Bialy and Mironov, that on the two torus there exist real analytic Riemannian metrics which are close to the Liouville metrics, and simultaneously they are different from them, and also non-zero analytic magnetic fields, such that the magnetic geodesic flow at a fixed energy level admits a polynomial in moment of first integral of degree 2. So as I have already said, that this problem reduces to this quasi-linear system, a u of x plus b of y is equal to 0, and the key idea to construct solutions to the system is as follows. We consider the following flow. This is the symmetry, or just a convoluted flow of the previous system with such matrices A1 and B1. And then we consider the Cauchy problem for this convolution flow, and we take as initial data just the data which correspond to the Liouville metric and a zero magnetic field. Of course, these data are solutions to the initial problem, and we deform them along this commuting flow. We obtain something, and after that we manage to prove that magic becomes no more than real ones, and also magnetic field appears, which turns out to be non-zero. So this construction allows to obtain some non-trivial solutions which are parameterized already not by constants, but two arbitrary functions, lambda1 and lambda2. Okay, so actually, could you please tell me how much time do I have?
Well, you started late, but yeah, you can have a few minutes more.
Okay, so maybe I will not go into details how one can construct some other solutions to this system. So I would like just to mention here that this system is proved to be semi-Hamiltonian, and it means that the generalized holograph method is applicable to construct its local solutions. So I will describe how it works. Just say that it was proposed by Sergei Petrovich in 1985, and I will just show the result. So we apply, together with Patashnikov and Shubin, we apply this method to the system, and also consider a commuting flow with cubic in the field variables components of these matrices, and we obtain that two of the unknown functions are in polynomial relations, and two left unknown functions satisfy these relations. So this is also a solution of the initial problem, but in an implicit form. And so we managed to prove that this system admits smooth local solutions which correspond to non-zero curvature metric, non-zero magnetic field. However, it is not possible to find explicitly f and j from these two functions, but we may make a change of variables going from xy to f and g in the known coordinates. And after that, we obtain explicit solutions, explicit form of magnetic field, magic components. And the first integral is a large form, so I will not have written them here. So this is about polynomial integrals. And okay, maybe I just skip the details and show you the results which correspond to non-polynomial first integrals, also at a fixed energy level. So we also consider this problem, and for the conformal metric we fix the energy level and search for the first integral, which is rational in momentum at this level. And this problem reduces to a certain quasi-linear system of PDEs which have some very well properties. It turns out to be semi-Hamiltonian. It can be written in the form of conservation laws. It also admits Riemannian invariance and can be written in the diagonal form. So it is possible to apply the generalized holograph method. However, we didn't manage to construct any solutions by this method. So we reduce this system to the following PDE by some to this PDE, and after that we apply the Legendre transform and the polar change of variables to obtain such PDE, which can be solved by the method of separation of variables, and finally we obtain some solutions which
could you stay a few seconds more on the previous slide?
Yeah, sure.
I just wanted to, didn't have time to understand. So it's it's linearizable then, yeah? You can, after change of variables,
we obtain just to this equation on the function psi, and we apply the Legendre transform, then one more change of variables, and to obtain this one.
Okay.
I skip any technical
Yeah,
details.
that's fine. Thank you.
Just one more minute, and I will start. And this equation can be solved by the method expression variables, and its solutions are represented in terms of hypergeometric functions. So these are non-trivial functions. However, for certain values of parameters, it can be reduced to elementary functions, and this is the final moment of my talk. I will just show a couple of examples which I managed to obtain. So for such solution, which is we obtain the following metric, which lives on the cylinder, and the following magnetic field, and the rational first integral, which conserves at a fixed energy level. One more example is written here, the following metric and the following magnetic field, and the very complicated first integral, which I will need here. And okay, I skip this, and thank you for your attention.
Okay, thanks very much for an interesting talk. Are there any questions or remarks? Вопрос? Please.
Сережа, у меня вот какой вопрос. Вы в основном, это Максим говорит, вы в основном интересуетесь, ну, я имею в виду то, чем вы раньше занимались, это глобальное решение. Вот вы могли бы мне сказать, например, вот вы находитесь на Торе, у вас задача связана с построением замкнутых геодезических. Вот там ситуация как выглядит? Вы строите решение, и из каких соображений вы утверждаете, что такое решение, оно является именно замкнутой геодезической? Там какое-то условие на периодичность решения. Вот как это может быть обобщено, например, когда у вас там многомерный тор, там, наверное, не периодическое решение, а квазипериодическое решение там тоже, чтобы была замкнутая геодезическая, нужно, чтобы тоже было замыкание такой траектории. Вот как это выясняется?
Здравствуйте, Максим Валентинович, да?
Да.
Здравствуйте, спасибо за вопрос. Я по-русски, видимо, отвечу.
Да.
Ну вот я, насколько я помню, ни слова не говорил про замкнутость именно геодезических. То есть я как бы этот вопрос не исследовал. А что касается периодичности, ну вот мы смотрим на системы, да, которые вот появляются в этих задачах. Ну вот, например, вот эта, да, система. Тут, ну вот в этой конструкции Дорицы и авторов, тут видно, что вот эти вот функции S и R, да, можно подобрать константы, чтобы они вот были периодическими и так далее. То есть, что касается вот решений, которые здесь появляются, почему они остаются периодическими, ну вот потому что начальные данные, если мы выбираем периодические, потом вот сдвигаем их, да, до этого потока ну, для задачи каши, то вот там периодичность сохраняется, то есть...
Так вот я и хочу понять, из периодичности не вытекает замкнутость?
Ну, там же всегда бывают обмотки. Всюду плотные, которые не замкнутые. Ну, то есть это, мне кажется, в общем случае сложно сказать. Надо...
Ну хорошо, спасибо.
Okay, any more questions or remarks? Okay, in which case, Sergey, thanks again very much for an interesting talk. So we continue after the coffee breaks at, okay, we will postpone for 10 minutes, so we start again at 11:40. we are ready to start. So the first speaker of the after break session is Norbert Hunkunu, and he will be talking about geometry and probability on the non-commutative two torus in a magnetic field. So Norbert, you can start whenever you are ready.
Okay, good morning, colleagues. I'm grateful to the organizers for inviting me to give a talk at this conference. Thank you, Sotiris, for keeping in touch. So what are the motivations of my talk? Let's notice that the work by Braun, the collaborator, which introduced techniques from algebraic topology into the theory of operator algebras, greatly impacted the birth of the non-commutative geometry as developed by Alan Kohn in 1992 to 1904. So the non-commutative geometry then became an exciting dynamic research area in mathematics and physics. And our group also contributed to this field in last decades. So the Gelfand-Leimark theorem, which gives an anti-equivalence between the category of locally compact Hausdorff spaces and that of commutative C-star algebras, is the starting point of non-commutative topology. And the correspondence is given by a map from a topological space X into the algebra of continuous complex valuable functions. And then we can formulate the following proposition. If we consider a commutative C-star algebra without identity, then there is a locally compact or non-compact topological space X such that the algebra A is isometrically isomorphic with the algebra of continuous complex valued functions. And every neighborhood in that topological space can be embedded in a compact set. There exists a point called infinity such that the union of that point with the topological space is compact. So if we define the space of continuous complex valuable functions with such condition on the, then everything's work correctly. And it is a commutative C-star algebra. But there is a price to pay. It is the definition of the identity function, which is not part of this algebra of continuous complex valuable functions. So the compactness here is identified through the presence of identity operator in the C-star algebra. So we say a C-star algebra is a non-commutative topological space, and it is compact if and only if it contains the identity. Let's notice that the Fourier analysis for the non-commutative N torus in a magnetic field was extended by Sakamoto and Tanimura in 2003. They studied the solutions of the Schrödinger equation in a uniform magnetic field for the non-commutative N torus, solved the eigenvalue problem of the Laplacian for the magnetic torus, and provided simple forms for all eigenfunctions. And the effect of perturbation by inner derivation on the quantum stochastic process and geometric parameters like the volume and the scalar curvature in the non-commutative two torus was studied by Chakraborty and collaborator in 2003. They perform a homological calculation showing that such a type of perturbation produces new spectral trips. They also obtained for the Weil C-star algebra the Laplacian associated with a natural stochastic process, and they computed the associated volume form. So my talk is motivated by all these works on the torus, and I'm answering the question how to characterize the geometric parameters and the probabilistic properties of a non-commutative two torus in a uniform magnetic field. So quickly, I will give an overlook on known result, and then I will present the main result and conclude the talk by giving some references. We consider a finite dimensional real vector space V equipped with a positive defined inner product. We denote by theta an irrational number in the interval 0, 1, and the irrational rotation star algebra d theta is, by definition, the star algebra generated by two unitary symbols x and y. And there exists a continuous action on the two torus on a d theta by star algebra automorphism alpha x, defined by the relation to here N1 and N2 are elements of Z. We denote by d theta empty the space of smooth elements for this action. That is for which the map of element X into the action of the automorphism alpha X on A is C empty. So d theta if empty is a dense subalgebra of D alpha and can be described by the space of the elements as combination of the product of a symbol X and Y in power n. Here an1 and 2 are reals, constants, rapidly decreasing coefficients. So there exists a unique faithful trace phi on the algebra d theta that is defined in this way, A0 are these constants, decreasing coefficient. So we consider the inner product through the trace phi, u and v element of the algebra d theta, and then we define the derivation, the dj associated to the group automorphism alpha x, given in this way. Actually, d1 acts with non-zero value on x, on the symbol x, and d2 give a non-zero d2 of the symbol y, give y when d2 of the symbol x equals 0. So for almost all theta, a derivation is of the form d, defined through the canonical derivation, the derivative dg, and the left representation are dots, with bg a complex number. So the dj's are the analogs of the differential operators acting on smooth functions on the ordinary torus, and defined in this way. We define the Laplacian delta as the combination of the canonical derivatives. All the above derivatives are studied in the Hilbert space H, and the canonical derivatives are self-adjoint on their domains. We denote by BH the space of bounded functions on H, and dr, the derivative dr, in this way, with the property dr star equal dr star, element of the space of bounded functions on the Hilbert space H. Now, denote by L0, the non-commutative unperturbed Laplacian, and L, the non-commutative perturbed Laplacian. So the magnetic Laplacian is defined through the canonical derivative and the gauge dk. Here, beta k are real numbers, and phi Gk are integers with the property skew symmetry property by interchanging the indices. And of course, Gk is a metric. With the quantum stochastic differential equations for any element of this algebra is established and has a unique solution, GT0, with which is a star homomorphism defined for the group automorphism action on element X, where W1 and W2 are the components of the classical Brownian motion. We have here the vacuum expectations expressing the dynamics of unperturbed systems. And the unperturbed non-commutative and perturbed non-commutative magnetic Laplacians in non-commutative two torus are given respectively this way, expressed through the canonical derivatives and the gauge Gk. And the perturbed magnetic, it is defined the same way, but here replacing the canonical derivatives by the derivative delta k. So ds, dsm are defined for the gauge and the canonical derivation. And the relation between the non-commutative magnetic Laplacians and the ordinary non-commutative Laplacian is given simpler for the term T GK0 expressed for the gauge and the canonical derivation dg. The same for the perturbed non-commutative magnetic Laplacian. Here, the term T Gk is expressed for the derivative delta G and, of course, for the gauge Gt. And the volume and integrated scalar curvature in these torus are given respectively by the relation 26 and 27. Then here, Tm is the magnetic heat semigroup, and Tr is just the trace. So we obtain that the volume of V of this algebra is invariant under the perturbation from the Laplacian, from the magnetic Laplacian unperturbed to the perturbed magnetic Laplacian. And the integrated scalar curvature is not invariant under the same perturbation. So only the volume is invariant under this perturbation. Now, the operator defined in this way is a self-adjoint operator on the algebra, the subalgebra, a sister algebra, d theta if d. We define the unperturbed magnetic operator G0M by these matrices with extra non-null, extra diagonal non-null elements. And the perturbed magnetic operator is defined in this way, R being an element of the algebra. And using the cone definition, H here is the Hilbert space, L1 empty of H, the space of compact linear operator T on H with this norm, finite norm, where mu I of T are the eigenvalues of these operators. So this trace for positive operators T is defined in this way by Lincoln in his book. We exploit also the definition of unperturbed and perturbed volume forms. And then TRW is here, the Dismer trace, and height dm is expressed for the magnetic operator dm in this way. Then we obtain that the volume form is invariant and that the perturbation from L0M to LM. And now let's define the spectral trip. An even spectral type for a star algebra A is a type P HD together with a Z2 gradient gamma such that the map of pi is a representation, and the operator D is an unbounded operator such that these properties is satisfied, and the commutator D with pi A is bounded. Then the trip defined with the operator D0M is an unperturbed magnetic, even spectral trip. And the trap defined with the operator dm is a perturbed magnetic, even spectral trap, with the gradient denoted by diagonal terms for the identity. And the star representation pi x, given x identity for x element of D. Then the following remark holds, these relations holds with gamma 1 and gamma 2, the 2 by 2 Clifford matrices. And let's now define Km, the vector space of all magnetic derivatives on this algebra, and B, any norm T theta infinity model for the derivative of this vector space of magnetic derivatives. We consider the contraction C delta M from this tensorial product, B tensorial product with Km into the B, the norm D theta infinity model. The magnetic connection is a complex linear map defined this way, such that this relation holds, or equivalently by this relation, where alpha J are just a combination of the gauge GG. So this map is a magnetic connection if we have these relations, that is the tensorial product of these quantities is expressed for the gauge and the derivative dg this way. So the curvature to form associated with the magnetic connection is defined by the usual relation. And the curvature to form associated with the magnetic connection is not invariant under the perturbation by inner product, derivative. Indeed, we obtain an extra term composed with the gauge and this derivative, this commutator. That is the extra term we obtain through such perturbation by the inner product. And then we obtain the following results. The magnetic quantum stochastic differential equation for X admits a unique solution, F0T, which is a star homomorphism defined for these relations. And here, F0t is just the primitive of F0t. Moreover, the vacuum expectation in the Fock space is given through the unperturbed systems and the quantity F0t. And the magnetic quantum stochastic differential equation in the tensorial product of the Hilbert space and the gradient gives, by this gradient, has also a unique unitary solution. And setting this FT in this form leads to the following magnetic quantum stochastic differential equation in form of the relation 48. Furthermore, the solution of this magnetic quantum stochastic differential equation and the vacuum expectation are given simpler by the relation 49 and 50, respectively. Ft is here, so the primitive of Fdt. And the solution of the quantum stochastic differential equation. So let us now generalize the magnetic quantum stochastic differential equation in 2D dimensional and non-commutative space and study some property of its solutions. So we denote here by CC empty the set of smooth complex valuable function on R2D with compact support. We consider the representation of the Weil relation, 51 and 52, with alpha beta element of R2D, F is a smooth function, and alpha dot x is the usual Euclidean inner product defined on RD. Then consider J and PG are the generator of V beta and UV respectively, viewed here as the position and momentum operators in the above representation. Then the unperturbed non-commutative magnetic Laplacian is given simpler for the quantities T tilde GK defined through the operators PG and the gauge GK. And then we consider the case when D equal 1 and the magnetic quantum stochastic differential equation is by simpler relation. Here, Y0 is the identity. And the magnetic quantum stochastic differential equation has unique unitary solutions. If we set these relations for all elements of d theta, of the algebra d theta empty, HT satisfies the magnetic quantum stochastic differential equation 56. And the vacuum expectations are given by simpler through the dynamics of the perturbed Laplacians and HT of R hat GK.
Number, you have a couple of minutes more.
Okay. So we define the vacuum expectation for the unperturbed systems. And in addition, for GK, we get these relations, 16.
What is MQSD solution?
What is?
MQSD solution.
The solution is...
you used it earlier as well. this this short.
I gave it earlier. You mean the solution of
Yeah,
this one,
the initials
or
SQD, what MSQD.
the initial one?
No, the initials. You wrote it in.
In 2D or?
No. Okay, if you go back to your slide where you were.
Where I was.
Yeah. You write properties of the MQSD solution. Remind what is MQSD.
Quantum stochastic differential equation.
Oh, I see.
Magnetic quantum.
Yeah, I see. Okay, sorry.
So we obtain the vacuum expectation in this form. Of course, in the formula 559, this is related to the ordinary unperturbed movement. Okay?
Yeah,
so,
sure.
Yeah? What is your question?
No, sorry. No question.
Okay. So, we obtain the invariance of the volume and volume form of non-commutative two torus under a perturbation by inner derivation of the magnetic Laplacian operators. And we derive here the magnetic quantum stochastic differential equation associated to this magnetic Laplacian, and computed and discuss vacuum expectation of the solution to the magnetic quantum stochastic differential equation in a non-commutative to the 2D dimensional space. So thank you for your attention.
Okay, thank you very much for your talk. Are there any questions or remarks? Any questions or remarks from the online participants? Okay, in which case, Norbert, thanks again very much for your talk.
Thank you.
So if you could please stop sharing your screen so we can... Ghosh, are you hearing us?
Yeah. Just I'm going to share my screen with your permission.
Yeah, you please try to start your screen. Okay, perfect. We can see now. So the next speaker is Georgi Sharygin from Moscow State University, and he will be talking about the argument shift method in UGLD. So you can please start.
Yeah, thank you very much for the organizers for inviting me and giving me this opportunity to talk. I hope that my talk you'll enjoy it. It's a little bit last minute. I mean, there are some results which I included in the very end, which are last minute results, but I hope you will enjoy it. Okay, so let's begin with something very simple. I just want to, suppose we have Poisson manifold. M is the manifold and pi is the bivector. And being Poisson means that the Schouten bracket with pi with itself vanishes. In this case, we can define the Poisson bracket of two functions f and g on manifold just by substituting their differentials into the bivector. And the Schouten bracket, the definition of Schouten bracket property guarantees that the Jacobi identity holds for this operation. We shall denote by z sub pi the Poisson center of the Lie algebra of smooth functions on M with respect to this bracket. Let psi be a vector field on M, which verifies the conditions which are listed here. So first, when we take the Lie derivative of pi along psi, we get some non-zero bivector pi sub psi. But then when we do the second, the second time the same operation, we get 0. Sometimes this equation, this condition is called the Nine-Hurst equation, and one can show that if this Nine-Hurst equation actually holds, then pi psi is in fact another Poisson structure, Poisson bivector, which is compatible, compatible with the initial Poisson bivector pi. Okay, so that's more or less known. And the classical argument shift method, which was first observed by Mishchenko and Fomenko, which generalized the results previously discovered by Monakov, is that whenever you have two functions f and g in the Poisson center, and whenever you have a vector field psi which verifies this condition at the previous slide, their iterated derivatives of f and g with respect to psi will commute for all iterations possible and for all p and q. To prove this, it is not necessary to do any difficult computations or anything. You just take the equation which is in here, that this right-hand side is actually just the combination of the derivative of the Poisson bracket of f and g with respect to psi is equal to the sum on the right-hand side. And then you just iterate this operation and take into consideration that f and g are in the center, and then by induction, you get this desired property. And also you get the equation that the same functions actually commute for the deformed Poisson bracket. So this is actually a variant of the well-known Leonard-Magritte induction method, or you can put it by Hamiltonian structure method, which allows you to generate large commutative subalgebras and Poisson algebras. The following example is the motivating example, which actually was the origin of the whole story. Take M equal to just the affine space dual to Lie algebra. Then, as you know, every such M will have a Poisson bracket if it identifies coordinates with elements of the Lie algebra, linear functions are the elements of the algebra. Then we get this bracket on the level of coordinates. You can phrase it in terms of the Poisson bivector as follows. So you see the coefficients of the Poisson bivector are just linear functions in these affine coordinates with respect to the affine coordinates. Now, if you take any constant vector field, that is the vector field with constant coefficients with respect to the affine coordinates on G star, then the conditions listed at the first slide are automatically verified, just because when you compute some constant vector field with a linear function, it kills it when you do it twice, right? It's just something very trivial. So this gives you actually a large, you can even show that for generic psi, you can get maximal commutative subalgebra in the algebra of, in the Poisson algebra of functions on G star. And this is what we call the argument shift algebra or the Mishchenko-Fomenko algebra. We should consider the particular case of the Lie algebra. Our prime interest will be in particular case of the algebra GLD of the general linear function in D dimension. And as you know, it is generated by the elements Lij and Lpq, which verify these conditions. You also define the representations of Lij by these formulas where Eij are the matrix units. And in what follows, we will often work with the matrix L of generators Lij. Oh, by the way, I probably intentionally use notation Lij and Eij for the generator. So sorry for this slip of hand, but yeah, I think I have several times used Eij instead of Lij. It means that the universal enveloping algebra UGLD of this GLD is just given by, you can write it as the space of non-commutative polynomials in variables Lij modular this relation, actually. This algebra, the representations are and are bar extended uniquely to this algebra. And also you should, everybody probably knows that the universal enveloping algebra of any of the algebra is in fact a bialgebra, even Hopf algebra, if you consider the coproduct given by this very simple formula on the level of the generators. And then extended by, well, to obtain the homomorphism of algebras, right, extended further. The center of this universal enveloping algebra is well known, and it is also well known that actually for any Lie algebra G, the Poisson center of the algebra of functions as G on G star, and the center of the universal enveloping algebra UG are isomorphic as vector spaces, actually even as algebras, and the isomorphism, linear isomorphism between these spaces is given by the very simple formula, the so-called symmetrization map. It takes sigma of monomial in x variables x1 through xk and send it to all the sum over all permutations of these variables of the corresponding products of the elements in the universal enveloping algebra, and divided by p factorial just to make sure that they get no unnecessary coefficients there. By Poincare-Hall-Bit theorem, this map is a linear isomorphism, as I mentioned, and you can choose generators on the left and on the right more or less in the same way. For instance, on the left, you can take the elements which are even equal to the coefficients of the universal characteristic polynomial, right? Well, I omit the signs here from my notation, don't care about the signs. And then it can obtain the generators of the universe of the center of the universal envelopment just by symmetrizing these elements ck tilde. Alternatively, you can take the matrix L of generators of UGLN, of UGLD, and take the traces of symmetrized, of powers of this algebra, of this matrix. And you get nice elements in the center, generators of the center of UGLD. So the main question which we address here is there a way to raise the commutative subalgebra in this SGLD, the Mishchenko-Fomenko subalgebra, argument shift subalgebra, to a commutative subalgebra in UGLD? More generally, I'm looking for a procedure similar to the shift in the quantum world, such that we can obtain such algebras for quantizations of any Poisson manifold, not just for Lie algebras. As far as the first question is concerned, there have been several results in this direction, several positive results. I can mention works of Alexei Tarasov. I think Alexei, I don't remember. There are two Tarasovs, and I always confuse them, sorry. Leonid Rybnikov, Alexander Molev, and a few others. In these works, the answer to this question appears from constructing explicit elements that correspond to the shifted generators of the center, especially when you take the generators of the first sort, that is the symmetrizations of the coefficients of the characteristic polynomial. For instance, in particular, in the papers of Alexander Molev and his co-authors, there are given explicit list of generators in quantum argument shift algebras for all classical series of Lie algebras. Summing up the results of the authors, which I mentioned, we have the following statement. For any psi in G, there exists a quantum argument shift algebra, A hat sub psi, commutative subalgebra, which which is sent by desymmetrization into the usual argument shift algebra. And this algebra is actually unique. This uniqueness result is very important for us. It is due to Rybnikov, and we can say that the algebra A hat is actually uniquely determined by its quadratic form with respect to the natural filtration in UG. Quadratic part, sorry. It's actually, in fact, it's just the centralizer of the quadratic part. Well, in spite of this activity and positive results, the nature of shift in itself is quite mysterious, and there has been no approach to the quantum shift on the level of algebras, of universal enveloping algebras. And I'm going to shed some light on this question in this talk of mine. So we suggest, as Yasushi Ikeda mentioned yesterday, to use Gurevich, Pyatov, and Saponov's quasi-derivations Dij or bar Dij on the universal enveloping algebra UGLD. I'm going to go in to speak about the motivation or about the way these elements actually appear, but you can just give the simplest way to define this Dij. There are different ways to define them, but the simplest way to define by far is by axioms. So you just list three axioms. The first one is just the scalars are killed by partial derivatives. The second is the normalization condition, that when you apply it to the generators, you get just deltas. And the most important part is the modified Leibniz rules. There are two different ways to write these modified Leibniz rules, so I prefer the first one. To prove that these three axioms work, you can actually check it very naively just by taking, I'm sorry, I think I need to, like this. You can check it very naively just by applying DAB to the generating, the relation that you need to verify, and checking that it is skewed. And actually, this is more or less what Yasushi explained yesterday. So today I will probably give a couple of other definitions, or alternative definitions of these operators. For instance, you can define these operators by the following method. You take the operator D, capital D, that sends UGLD to matrices with coefficients in UGLD just by applying partial derivatives at the ijth. Ijth partial derivative stays at the ijth place. Then it turns out that the map 1 plus D, that is, you add the identity matrix to D, is equal to the following composition. You take UGLD, you co-multiply the elements, and then you apply the representation to the right leg of the tensor square. Then this is a very convenient way to define, because you can actually extend it to other representations and to other Lie algebras. Here is yet another way to define these partial quasi-derivatives by saying that you take symmetrization map, invert it, and then you get a map from symmetric algebra of GLD, first to universal enveloping, and then to sigma minus first. And that is equal to the exponential map, the differential operator on SGLD, matrix value differential operator, which is equal to just the exponent of the matrix of partial derivatives of SGLD. So one can also, again, extend this definition by modifying this exponential map to something else. So there is lots of modifications that can be done here. So the main conjecture which we worked on for a couple of years is the following. For any coefficient matrix psi, numerical matrix, if we consider this operator, then for every element f and g in the center of UGLD, we have this commutation relation for all p and q. There were several facts that supported this conjecture. First, there were several computations in low dimensions made by Yasushi. Then Yasushi managed to prove that when you take P and Q equal to 1, this formula actually holds, and that will be an important step in our proof further. And the third fact, which I proved actually this winter, last winter, was that if you apply this F and G to this chosen set of generators, then this condition will also hold. So today I'm going to speak about the theorem which we published in this paper, well, in July, that actually claims that this condition, this conjecture, holds that for any F and G, for any P and Q, and any Xi, this commutation relation is true. So the proof, I'll sketch it because I don't have much time, I'm afraid. The proof is pretty straightforward. We just take the following theorem, which you can, well, which is due to Rybnikov. I mentioned this already, but in case of DLD, you can actually write down the elements in quadratic part of the algebra very explicitly. So here is the theorem in this particular case. So let Xi be a diagonal matrix with distinct eigenvalues. Then the algebra A hat sub Xi, if it exists, is equal to the centralizer of the elements EII. I told you that I will probably go from Lij to Eij. I'm sorry for this, but it's kind of slip of the hand. And of the elements Tk of Xi, they are equal to this combination of quadratic elements in the universal enveloping algebra. Well, so since we know that A hat sub Xi actually exists, we see that the centralizer of the elements Eij and Tk of Xi, Eii and Tk Xi in UGLD is commutative. That's a very important result, very interesting and very helpful actually. So if we want to prove that our elements F and G for F and G commute with each other, it is just sufficient to show that the iterated partial derivative, quasi-derivative, commutes with all Eii and all Tk Xi. Well, the general case is reduced to this case where Xi is diagonal just because we can actually diagonalize almost any matrix by conjugation. Since this conjugation actually preserves the form of the operator, but it can make the matrix diagonal. And since almost every matrix, well, since the space of matrices which are diagonalizable is dense in the space of all matrices, we are able to prove, we can go on by continuity and prove that everything commutes whenever we want it to commute. So it's sufficient to consider diagonal matrix Xi. And now the proof goes on by induction. For instance, if we want to prove that this Xi P of F commutes with A, let's assume that, commutes with EII, let's assume that A commutes with EII, right? And differentiate this equation by Xi. And through several lines, we obtain this expression. And one can check that the same expression can be obtained if you apply this Xi to the opposite order of the factors. So this closes the problem with EII, and as far as Tij, Tk are concerned, we really need to work a little bit more. So we also do this by induction. The first step is to observe that under the conditions we impose, the positive derivation of any element Tk of Xi is scalar, and then the general case is reduced to the following lemma. For any x in UGLD, so the center of UGLD is in the module of all x's, in the space of all x's, for which this trace is equal to 0. So here we have two matrices. We take the commutator of the matrix multiplied by, sorry, it should be capital Xi here. It should be capital Xi here. Multiplied by Xi, and then it should be equal to 0. And moreover, this module is invariant under the action of the quasi-derivation d hat Xi. So now we do the same inductive procedures, go on step by step, use this lemma, and this completes the proof. Actually, the first step, that X is in the center, that center is in this, is based on the description of the center given by Yasushi, and I mentioned it some time ago. So that's actually the proof. And I conclude my talk with, well, few observations and speculations on the subject. So first of all, we don't know how to prove the commutativity of the image of this operator unless we use Rybnikov's characterization result. So it is quite an interesting problem if it is possible to prove this independently of Rybnikov's description, because the original proof by Mishchenko and Fomenko, it didn't demand anything, just the shifting and anything, nothing else. Second, the algebra A hat sub psi, always generated by partial psi, is not preserved by this operator. That is to say, if you take elements of in A hat sub psi and apply this operator to them, you will not get any more into this algebra in general. Further, if you try to extend this construction from GLN to LD to some other Lie algebra, by embedding this Lie algebra into GLD for suitable D, and then restricting the operations from UGLD to this embedded algebra, well, it is possible to do, but unfortunately this does not work. Actually, the analog of this result, which I just talked about, does not hold. There are counterexamples. However, if we carefully choose a good set of generators for the center of this UG, of this universal evaluable algebra or some other algebra, then the argument shift, this operator dxi, will still send these generators to themselves, and thus, in some sense, these restrictions of dxi will generate the argument shift algebra for arbitrary classical series. You can see this in our very recent paper. I think it was published a couple of days ago on the archive, joined with Alexander Molev. Okay, that's more or less all I wanted to say. Thank you for your attention, and I hope you enjoyed my talk.
Okay, thanks very much for an interesting talk. Are there any questions or remarks? Could you please clarify what means a good set of generators?
The good set of generators are the generators similar to the symmetrizers of the coefficients of the cubistic polynomial. They have lots of properties which do not hold if you go from these generators to the traces of LK. They are much easier to work with, and when you differentiate one of them, when you take partial derivatives of one of these operators, you more or less get a linear combination of other generators, so you can make some inductive steps with them. That's what differs them from say traces of powers of the generators matrix.
Thank you. And when you had the commutator equals 0 for PQ more than 0 or equal, Yasushi proved for Q equals 1, yeah? And
Yasushi proved this for PQ equal to 1. He did this by a careful description, I think, of the image of the operator D sub psi of F on the center. It is possible to show that this image is generated by a very special set of elements, something like, I think I can draw it here, right?
Mm-hmm.
Just a moment, I think I can draw. Yeah, I think I can draw. Something like by trace, I'm not good at drawing, of this psi matrix times L to the power K. Sorry. I think it's a little bit distorted. I'm not used to drawing at least.
Mm-hmm.
So this is the image of, I think Yasushi mentioned it yesterday, the image of the first degree operator xi is generated on the center. It's generated by these type of elements, and it is, so you can actually use this description to prove the result.
Mm-hmm. I see. And And for the rest, actually, you don't. It's a conjecture, but you tried until up to what P and Q.
Sorry?
For the rest is a conjecture. So have you tried for?
No, this is proof. I mean, for GLD. For the, you mean we don't know how to describe the image of DP psi? Yes, that's quite a big problem. Yasushi managed to describe the image of DP psi in degree 2, which gives you a set of generators of the argument shift algebra up to the second degree of the shift. And it is interesting that they actually match somehow the elements earlier described by model by totally different methods. But in general, the role of the separators d psi and how they act and their relation. These argument shift methods, argument shift algebras, quantum argument shift algebra, has been studied for a long time, and there are relations of this algebra, for instance, to the Youngian theory, the Youngians. And it is interesting whether one can actually erase the operator d psi or just general operator d ij to Youngians. It is not quite clear. The formulas which Yasushi wrote yesterday, they resemble something you obtain in Youngians, but the actual relation of these constructions are still mysterious. The extension to Youngians is important if we want to explain why, in fact, these operators give you commutative subalgebra, and if we can explain that, we probably have know a way to extend them to other classical algebras without losing this wonderful property. Because the naive way actually gives us some, partial result.
I say thank you. I hope you can probably tell us more about this kind of seminar. Okay. Thanks again very much for your talk. So the next speaker for today is Alexander Smirnov, and who will be talking about Dubrovin's method for MKDV hierarchy. So, Alexander, where are you with us?
Меня слышно?
Да, слышно. Попробуйте, пожалуйста, продемонстрировать ваш экран. Прекрасно все видно. Можете начинать, когда вы готовы.
Поскольку мы опаздываем, с вашего разрешения я по-русски буду говорить и
Хорошо.
побыстрее все это делать. На самом деле название я сделал давно, а, так сказать, в процессе подготовки немножко задача изменилась, так что тема будет чуточку итоговая другая. Значит, вот хорошо известно, что есть преобразование Миура, которое связывает уравнение Картавега-де-Фриза и модифицированное уравнение Картавега-де-Фриза. Соответственно, хотелось знать, как связаны их спектральные кривые, конечнозонные решения. И поскольку конечнозонное решение уравнения Картавега-де-Фриза хорошо давно известно, а вот лично для меня модифицированного уравнения Картавега-де-Фриза нет, неизвестно именно вот такого действительного. То есть комплексно, понятно, есть формула Котлярова-Итса, которая дает иерархию, решение иерархии КНС, конечнозонное решение. Вот я решил сделать такую задачку. Значит, кое-что вот напоминаю, как именно получается, значит, преобразование Миуры, как оно связывает между собой потенциалы оператора Шрёдингера и потенциалы оператора Лакса с матрицей второго порядка и с вещественными коэффициентами. Значит, теперь, если мы рассматриваем конечнозонный потенциал оператора Шрёдингера, то есть уравнение Апеля, которому удовлетворяет произведение двух собственных функций этого оператора. В случае конечнозонного потенциала это произведение является многочленом по спектральному параметру. Значит, коэффициенты этого многочлена удовлетворяют рекуррентным соотношениям, которые еще называются уравнениями Новикова. Значит, вот такие вот у нас есть рекуррентные соотношения. Хорошо, давно уже всем известны. Дальше, интегрируя, мы получаем вот выражение этих коэффициентов через интеграл, опять же, давно хорошо известные, с которыми связано уравнение из иерархии Картавега-де-Фриза. И в случае вот конечнозонного потенциала или конечнозонного решения уравнения Картавега-де-Фриза вот выполняется уравнение Новикова, которое вот здесь вот наверху написано. Тоже всем давно хорошо известно. Дальше, опять же, хорошо известно, что если мы берем с помощью этого произведения по такой вот формуле, достаточно простой, можно найти уравнение спектральной кривой, соответствующее данному конечнозонному потенциалу. Дальше, теперь, если перейдем к оператору лапс для уравнения МКДВ и рассмотрим матрицу М, удовлетворяющую такому соотношению, строим рекуррентные соотношения. Рекуррентное представление для матрицы М через матрицу В. Получаем, что матрицы В имеют следующую структуру. Между элементами матрицы В у нас возникают ниже написанные рекуррентные соотношения. Поскольку V у нас вещественная функция, то у нас возникают условия вещественности на эти элементы. У нас все нечетные F обращаются в ноль элементы. Все четные H, совпадающие с четными G, являются действительными. Нечетные H отличаются от G знаком и являются чисто мнимыми. Значит, вот несколько элементиков этих матриц тут у нас с вами написано. Значит, из того уравнения на матрицу М, которое было написано выше, вытекают стационарные уравнения, на которым удовлетворяют многофазные решения. В отличие от случая КДВ, здесь у нас два стационарных уравнения. Поскольку G и H связаны условиями вещественности, то они распадаются вот на такие два соотношения. Вверху у нас только четные индексы остаются, а внизу только нечетные индексы. Дальше строим второй оператор для пары лакса с помощью матрицы V в таком виде, то есть четными по порядку матрицами V. Значит, если брать матрицы V с нечетными индексами, то у нас эта пара лакса не совместна, то есть оставляем только четные. Условия совместности имеют следующий вид, и, соответственно, эти условия совместности дают нам интегрируемые уравнения нелинейные и из иерархии модифицированного уравнения Картавега-де-Фриза. Значит, спектральная кривая получается вполне естественным образом. Это характеристическое уравнение матрицы М. И вот теперь встает вопрос. Вот у нас есть одна иерархия, другая иерархия, одна спектральная кривая, другая спектральная кривая. Как они между собой связаны? И вот мы сейчас с вами посмотрим. Значит, вот интегралы И из иерархии КДВ связаны с элементами матрицы М иерархии МКДВ с помощью следующих равенств. Дальше, используя рекуррентные соотношения, одни, другие, уравнения на h, которые легко... Мы получаем, что это связь между интегралами уравнения Картевега-де-Фриза и элементами матриц модифицированного уравнения Картевега-де-Фриза, она сохраняется для любых n. Вот с использованием таких соотношений. Дальше, используя все эти равенства, мы видим, что дифференцируя по t соответствующим решению уравнения обычного Картевега-де-Фриза, заменяя на v, проводя преобразование, получаем то, что было у нас и раньше. То есть зависимость от t у нас сохраняется как и для обычного Картевега-де-Фриза, так и для модифицированного Картевега-де-Фриза. То есть они полностью у нас идентичны. И, то есть преобразование Миура связывает между собой решение всех уравнений иерархии. А это означает, что у нас есть глубокая связь между конечнозонными решениями одной иерархии и другой иерархии. Ну, теперь несколько примерчиков, которые нам немножечко помогут побыстрее все это сделать. Значит, полагая n равен единицам, матрица M имеет следующий вид. Вот у нас спектральная кривая. Первые старшие коэффициенты зависят от коэффициентов разложения матрицы M. Младшие являются интегралами от функции v. Стационарные уравнения в данном случае имеют следующий вид. Вот у нас два уравнения, одно с счетными коэффициентами, другое с несчетными коэффициентами. Подставляя конкретно, получаем следующее равенство. Нетрудно, вот из последнего этого равенства видно, что у нас либо c1 равно нулю, либо v постоянно. В принципе, странный случай, но все работает. Вот у него спектральная кривая. Находим u, его решение. Вот, соответственно, спектральная кривая. Видим, что вот у нас спектральные кривые отличаются на множитель с квадратиком лямбда плюс c1 в квадрате. А дальше, если лямбда квадрат заменим на e, у нас получается ровно то, что здесь и написано. Если c1 равно нулю, а v не является постоянной, тогда функция v является либо эллиптической, из-за знака четвертой степени, значит, это либо синус эллиптический, ну, либо у нас вырождение происходит. Значит, вот у нас спектральная кривая в таком случае имеет вид. Произведение собственных функций оператора Шрёдингера такое. И вот ее спектральная кривая. Видим вполне хорошее согласие этих спектральных кривых. Отличается на e, все остальное лямбда квадрат заменяем на e, получаем все то же самое. Значит, вот у нас решение выписано, но не знаю, стоит ли сейчас на этом останавливаться, но вот есть решение уравнения МКДФ, соответствующие два решения уравнения КДФ, и должен сказать, что они имеют одно и то же вот спектральную кривую. То есть у нас вот эти два решения связаны между собой из-за спектральной деформации, ну, которая, по сути, представляет собой сдвиг на полупериод тора эллиптического, при котором либо синус, либо дельта амплитуда меняет знак. Значит, вот у нас спектральная кривая этого эллиптического решения, корни у нас действительные, хорошие. И то же самое там было с Е. Ну, с Е понятно. Если делаем вырождение в King, то спектральные кривые тоже вырождаются, а при этом вот эти решения уравнений Картавега де Фриза становится довольно забавно. Одно идет в постоянную величину, а другое идет в солитон. При этом спектральные кривые у них, в принципе, одни и те же, с точностью до интерпретации. Да, вот e квадрат в одном случае можно убрать в W, тогда получается решение постоянное. Либо навешиваем эту точку, возникает солитон. Значит, здесь у нас анализ при n равном 2. Происходит вот тоже два стационарных уравнения, и тоже есть разные варианты. Но для экономии времени я говорю, что самый правильный вариант, когда все нечетные индексы мы обращаем, все c с нечетными индексами обращаем в ноль и смотрим только на второе уравнение. Хотя там тоже у нас рассматривалось все это. Значит, вот если нечетные индексы не 0, у нас вновь возникает это выражение лямбда плюс c1 в квадрате и множитель спектральный и многочлен, который переходит на многочлен, определяющий спектральное уравнение конечнозонного решения Картавега де Фриза. Если же мы полагаем c1, c3 равно нулю, то есть избавляемся от первого уравнения стационарного, оставляем только второе, у нас получается спектральная кривая имеет род 2, а вместе с тем функция имеет род, является эллиптической, либо ее вырождением. В качестве примера было взято вырождение. Значит, вот такое решение модифицированного уравнения Картавега де Фриза, соответствующему спектральной кривой, опять же, с действительными корнями всеми на оси. Значит, вот этому решению модифицированного уравнения Картавега де Фриза соответствует два таких решения Картавега де Фриза. И вот нетрудно сравнить, что с точностью замены лямбда квадрат на e мы получаем те же самые спектральные кривые. Способы вычисления я раньше сказал. Ну и вот теперь подводим, в принципе, некоторые итоги тем наблюдений, которые мы и сделали. То есть если брать спектральную кривую для конечнозонного решения модифицированного уравнения Картавега де Фриза, то оно вот должно иметь такой вид. То есть справа должна быть многочлен от лямбда квадрат с действительными корнями. Вот это такие наблюдения. И, значит, это с двумя инволюциями. Гиперэллиптической инволюцией и инволюцией, меняющей лямбда на минус лямбда. Наличие этих двух инволюций приводит к тому, что спектральная кривая гамма накрывает две другие кривые. Значит, одна кривая и вторая кривая. Когда они являются нечетной степени по спектральному параметру E, они подходят для конечнозонного решения уравнения Картавега де Фриза. Значит, вот мы там видели, да, вот когда было n равно единичка, тогда у нас было E и плюс вот этот добавочка. Когда n была двоечка, у нас был сам многочлен. Соответственно, из пары Лакса, из второго оператора пары Лакса мы получаем следующий вид абелевого интеграла второго рода, имеющего нужную асимптотику. Ну и теперь, подводя итоги, могу сказать, что имея эти данные, уже можно по схеме Кричевера, либо, скажем так, ну, Кричевера Дубровина, да, либо, что более проще, Ица Котлярова, построить функцию Бейкера-Хейзера, потому что тут всего 2 на 2. Принцип тот же самый. Осталось только уточнить положение полюсов этой функции Бейкера-Хейзера и провести редукцию многомерной тета-функции за счет того, что у нас есть инволюция. И в итоге получить окончательную формулу для конечнозонных решений модифицированного уравнения Картавега-де-Фриз. Ну, в принципе, вот о чем я хотел кратенько сказать. Хотел, конечно, побольше, но вот, к сожалению, через 5 минут у меня уже студенты начинаются, так что вот вынужден на этом закончить. Спасибо за внимание.
Спасибо большое. Есть вопросы или замечания? Да, конечно.
Саша, привет. Это Максим говорит. Вот
Да.
твой доклад очень интересный был, я с большим удовольствием его послушал, но вот есть одно предложение, которое, вероятно, тебе тоже будет не бессмысленно. Значит, вот ты рассмотрел переход от КДВ к МКДВ, рассмотрел, как все меняется при этом переходе. Это вот, я говорю, очень для меня было интересно по одной причине. Дело в том, что сейчас эта тема стала снова очень востребована, появилось много работ по солитонному газу, и в том числе для уравнения модифицированного Картавега-де-Фриз. То есть как бы это очень актуальная задача. Там отличаются сценарии от ситуации именно с Картавегом-де-Фризом, поэтому те, кто работает в этой области, им это очень интересно. Но есть еще одна задача, про которую я тебе хотел сказать. Дело в том, что ты прекрасно знаешь, у тебя вот есть работы, посвященные нелинейному уравнению Шрёдингера.
Алло. Алло, не слышно. Алло, я не слышу, так что я...
Да, извините, просто у нас с микрофоном была проблема.
Понятно.
Да, так вот, и следующий коммутирующий поток в иерархии нелинейного Шрёдингера – это уравнение, которое называется комплексное МКДВ.
Ну, с комплексным там все понятно. Вот я другое здесь вижу, другое приложение. Во-первых, известный оператор Шрёдингера с эллиптическим потенциалом. Следовательно, используя вот эти связи, эти соотношения, можно строить, поскольку кривые уже понятно соотношения, можно строить оператор Дирака с эллиптическим потенциалом. А
да.
дальше, поскольку есть уравнения гойно-конечнозонные, то есть можно, так сказать, предложить фуксовые системы конечнозонные, используя все эти связи. Вот это вот то, что я вижу.
Ну да, хорошо, спасибо.
Вот, а вот пока что вот прошу извините, у меня в 13 часов пара, так что если больше нет вопросов, то я бы отключился.
Окей, хорошо, тогда еще раз благодарим. Спасибо.
Спасибо.
Okay, the next speaker in the final for this session is Anton Kazakov from Moscow State University and also the Yaroslav State University, and he will be talking about the solution of the black box problem for electrical networks via cluster algebras.
Yes.
Антон, да, тебя видим. Попробуй, пожалуйста, продемонстрировать экран.
Сотерись, если будет звук хуже, ты меня прерви тогда сразу.
Хорошо, нет, проблема со звуком, это с нашей стороны, микрофон не работает.
Ага.
Тебя прекрасно слышим. Тогда можно начинать, когда ты готов.
Хорошо. Firstly, I want to express my appreciation to organizers for opportunity to take part in this great conference. In my talk, I will try to reveal cluster nature of electrical network theory. Particularly, I will give a sketch of a new solution of the black box problem using cluster algebra for non-negative Grassmannians. my talk is based on just a moment, this joint article, and also I have to notice that recently this beautiful work by Terence has been published. My approach and Terence's approach share many common ideas, but we used quite another non-negative Grassmannians and tried to reach some different goals. But I have to mention also this beautiful book. Okay, firstly, I will briefly give examination on electrical network theory. An electrical network is just a planar graph, weighted planar graph. Its nodes are divided on two subsets. Subset of boundary nodes which light on a boundary circle, and in inner nodes. For instance, in this picture, you can see basic triangle electrical network. It has three boundary nodes and one inner node. And I have to notice that boundary circle doesn't belong to our electrical network. As I said, our graph have weights, and weights means conductivities. Conductivities, C, it is inverse to resistance. I will write that if my electrical network has n boundary nodes, that E belong to E big one N. We can apply electrical voltage which to boundary nodes, which induce voltage on inner nodes and electrical currents which run through all edges of our graph gamma. This voltage on inner nodes and currents could be defined by famous Kirchhoff's laws. It is the first, it is Ohm law and law of conservative flow from the each inner boundary, each inner node. So just a moment. The main object of electrical network theory is a response matrix. Consider an electrical network and apply to its boundary nodes voltages. This voltage induce currents running from boundary. In this picture, it is, let's say, for instance, this currents E1, E2, E3, and for instance, boundary voltage U1, U2, and U3. Boundary currents running from boundary nodes is just a sum of all currents running from edges connected to boundary node. Boundary currents related to boundary voltage by this formula. So some matrix called response matrix exists, and it relates boundary voltage and boundary currents as follows. It is a very special matrix. Every such matrix is symmetric. All non-diagonal entries are not positive, and each column and each column is a linear dependent. Not linear independent. Sorry, just a moment. The cornerstone problem of electrical network theory it is black box problem. Consider an electrical network on a given graph gamma, and we have to recover conductivities of all edges of our graph gamma using given response matrix of our electrical network. It is quite a difficult problem, and it is not clear that it is possible, but it is possible, and famous theorem that for every for every minimal electrical network, conductivity of every minimal electrical network could be recovered by its response matrix. Minimal, it's roughly speaking, it is electrical network without parallel edges and series edges, without such two cases. Okay, this problem closely related to famous Calderon problem, especially to famous inverse problem of electrical impedance tomography. What it means? Consider conducting medium in a disk. It means that in each point of our disk we have two functions: conductivity function sigma and a function of electrical voltage. And these two functions are related to each other by this differential equation. It is indeed it's just a continuous analog of Kirchhoff law, and we have Dirichlet boundary condition. It is just a boundary voltage applied to boundary of our disk. Boundary voltage, of course, induce boundary currents. Boundary currents in this case called Newman boundary condition. And suppose that for each boundary voltage, we know induced by it boundary currents. Formally, it means that we have an operator from Dirichlet condition to Neyman condition. And in this problem for electrical tomography, it just we have a conducting medium, and we know this operator from Dirichlet to Neyman conditions. And it is required to recover conductivity function sigma using this operator. As I said, this equation and this condition, it is of course continuous analog of Kirchhoff law and boundary voltage, and it is just boundary currents. And this operator, it is of course a continuous analog of a response matrix. And therefore, the common way to solve this problem, the inverse problem of electrical impedance tomography, it is to approximate our continuum medium using some discrete electrical planar network with a lot of boundary nodes. It is very typical electrical network which is used to construct a numerical solution for inverse problem of electrical impedance tomography. This network, by the way, might be seemed very special, but in fact, every general electrical network could be transformed using some electrical transformation to this network. So it is quite a general network. So therefore, it is important to fastly and stable solve the black box problem for electrical network. It is very important problem. And now I come to sketch of my approach to the black box problem. And firstly, I come from electrical network to non-negative Grassmannian. Consider an electrical network and define a point of Grassmannian n-1 to n by this formula. I have noticed that xij, it is entries of a response matrix of my electrical network E. This matrix define a non-negative point of Grassmannian n-1 to n. It means that every n-1 by n-1 minors of this matrix is non-negative. For instance, for any network with free nodes, I have the following matrix, and I notice that, as I said, entries, columns of matrix M, N, E is linear dependent, and rows of this matrix also is linear dependent, and I can eliminate any row vector of this matrix, for instance, this. And in fact, point of Grassmannian associated to my network defined by this matrix. Yes. Why every n by -1 minor of this matrix is non-negative? It is quite, it might be seemed very unnatural, but in fact, any n-1 by n-1 minor could be expressed in terms of flows or partition function of flows or partition function of almost perfect matching on some special graph associated with every electrical network. In next 3 slides, I wrote down a formal definition, but very roughly, with every electrical network, I can associate Postnikov graph, which could be constructed as follows. I draw on the same picture an electrical network. It is a triangle, and at the same picture, I have to draw a dual to this graph. It is a triangle. All new edges has weight equal to 1. I couldn't. I skip it. Okay, and I come to from black box problem to electrical network to black box problem for Postnikov graph. Consider Postnikov graph associated to our electrical network, and we have to recover weights of Postnikov graph using a matrix omega NE associated to our electrical network. Omega NE has the same information as a response matrix. It's just a extending of a response matrix. And the first step of this solution, main step, it is recover of weights of Postnikov graph up to gauge transformation. Gauge transformation, it is following transformation. Consider an inner node of Postnikov graph, and we can multiply on a positive number all weights of all edges connected to our node. So, and I go to solution, and I have to define a twist operation. It is a definition also might be seemed very unnatural, but it is just a generalization of Fomin-Zelivinsky Bernstein twist operation from the famous work about chimpanzees for upper triangle matrices. Probably I skip a formal definition, but informally it is just a special procedure of orthogonalization of columns of my matrix omega and E. For for instance, consider a response matrix for a triangle, triangle electrical network. Consider an matrix omega free E for triangle, and the twisted matrix associated with my network has the following form. Notice that this matrix also defined point of non-negative Grassmannian. It is quite a miracle. So, and how to recover weights of Postnikov graph up to gauge transformation. Using the Scott rule, I couldn't define it. It is a rule from Scott work about cluster algebra for non-negative Grassmannian. Using Scott rule, we label each face of Postnikov graph by minors of twisted matrices omega n e. For instance, for a triangle, we have to label faces as follows. It is also this rule. It is a simple generalization of Chemberry and that's by Fomin, Bernstein, Zelinsky. Then for each H, for each inner H, for instance, which connect only in H, we have to take a minus of faces which bordered by this H, and sorry, probably you couldn't see, and multiply this minus and invert them. And by this way, we have a weight of this H. And for H which connect boundary vertices within vertex, we have to take a label of closest counterclockwise face to our H. For instance, for this H, the closest counterclockwise face is this, and it is labeled by sigma 1,6, and weight of this H is equal 1 divided by delta 1,6. And so by this way, I have a weight of Postnikov graph up to gauge transformation, and making properly by some algorithm sequence of gauge transformation, I recover conductivities of electrical network which was given, because what I have to do, I have to, by gauge transformation, I have to make all additional weights of all additional edges to one. The theorem that it is possible, and I even think that there is a close, nice formula how to do it. But even without this step, it is another way to solve the black box problem, and I suppose that it is a very good strategy, because all classical algorithms principally non-linear, but in my approach we just calculate minus and solve linear systems, and it is numerical stable algorithm, I suppose. So thank you very much. It is about all.
Okay, Anton, thanks very much for an interesting talk. Are there any questions or remarks? Any questions? Okay, in which case, thanks again, Anton, very much. So we are late 20 minutes, so we meet after lunch at 2:20, just 14:20. The afternoon session. So the first speaker is Pavlos Kostakis from the University of Warsaw, and he will be talking about matrix factorization, Young-Baxter, and Pentagon maps. So Pavlos, you can start whenever you are ready.
Okay. Thank you very much, first of all, Sotiris, for inviting me and, of course, giving me the opportunity to talk one more time in Yaroslav. And thanks a lot for that. Okay, so, and of course, all the organizers. So today I'm going to speak about this title, Matrix Factorization, Young-Baxter, and Pentagon Maps. And well, actually, this is a work that well, it was introduced, well, it was initiated during the pandemics. And well, I think it's quite interesting and I quite like it somehow. So, well, I'm going to start actually my talk with a small introduction. Then I'm going to speak about some preliminaries about notation and stuff like that. And finally, we'll say about my result on Pentagon maps and Etuanic Pentagon maps. Okay, so the first time that I heard actually about Pentagon maps and actually about the Pentagon relation and about in general about the polygon equation, it was during the pandemics, and I owe that to Igor Korepanov that we had various discussions, and I must say he introduced me to this very interesting subject, and well, I thank him for that, actually. And so I'm going to say that the first non-trivial examples of the so-called hierarchies of polygon and simplex equations are the Young-Baxter equation as well as the Pentagon equation. Okay, they are very interesting equations. They appear in various places in mathematics and in physics. Specifically, let me speak very quickly about the first non-trivial example, this of simplex equations, and let me speak about the Young-Baxter equation. Well, actually, it appeared first in the work of Young and independently of Baxter. While actually Young was dealing with many body problems in quantum mechanics, actually one-dimensional n-body problems, and he wanted to, let's say, compute the wave function. Well, in his imposing Bethe ansatz, actually, at the end of the day, in order to be able to compute the wave function, he had some identities like this one that I have written here, they had to be satisfied. Similarly, work was in if I remember, from some split chains, and Baxter wanted to find the correlation function, and then he had a similar actually identities to be satisfied. And nowadays, these identities are called Young-Baxter relation. Well, in this equation, Rij serves as a linear operator, where V is a vector space, and the subscripts here indicate the two factors of the threefold tensor product on which the linear operator R acts non-trivially. Okay, a bit later, actually, this equation, Drinfeld introduced, actually proposed to look for the set theoretical version of this equation, where one replace the set X with any set without actually any structure pre-assumed on the set, and R to be just a map. And R is a map. Well, so actually now these maps are Rij, exactly as in the tensor version of the Young-Baxter identity, specify actually where the map acts non-trivially on the threefold, let's say, Cartesian product of the sets. Okay, so this is the equation. Just very quickly where it appears, and I give also an example here. It appears, as I said earlier, in quantum mechanics or in statistical mechanics by Baxter. Also, it has appearances in quantum group, in knot theory, and of course in discrete integrable systems. That is, I'm interested more, actually. And also I have to say that the solutions of the set theoretical version of this Young-Baxter equation are now called Young-Baxter map. This terminology was introduced by Veselov and Boosthaber. Well, I think the work of Veselov was in there. And what I have to say, and why actually for us in the discrete integrable systems community, why we're interested in Young-Baxter map is that some discrete integrable systems are naturally associated with Young-Baxter maps. And maybe the most somehow, famous or and simple example is the so-called Adler map that is given here. This is the form of the map where P and Q are, let's say, complex numbers. And this Adler map is related to the lattice potential KdV equation. Actually, the Adler map serves as can be seen as a generator of the discrete symmetries of the Veselov-Sabat dressing chain. And in a sense, it can also be seen as a discretization of the KdV equation for that respect. Okay, so this is the Adler map, it's a Yang-Baxter map. It satisfies the Yang-Baxter relation I introduced earlier. And also it's strongly related to the lattice potential KdV, that is a discretization of the potential KdV equation. All right, so this is very quickly the one example of Yang-Baxter maps. And also I have to state that actually in 2002, Veselov and Souris introduced lax pairs for some equivalent classes of families of Yang-Baxter maps. And actually they showed that, for instance, the Adler map is equivalent to the following refactorization problem that I have here, where lambda is a spectral parameter and L is this 2x2 matrix. So actually, the Adler map is equivalent to this refactorization problem that was given by, shown by Veselov and Souris. And also they actually proved, and actually they showed, they provided matrix factorizations are actually lax pairs for equivalent classes of families of Yang-Baxter maps. Okay, so that's the preliminary, the introductory stuff for the Yang-Baxter maps. And now let me move to the Pentagon equation. And Pentagon equation was introduced inside the context of conformal field theory and by Moore and Seiberg in 1989, as we have seen, and also by Milet in 1990, inside the context of three-dimensional, let's say, quantum integrable systems. This is how the equation looks. Again, Rij can be seen as linear operators with where the subscripts specify where the, let's say, the linear operator act non-trivially. And again, we have the set theoretical version of the Pentagon equation, where now Rij are considered as maps, where again the subscripts define where the map R acts non-trivially on the threefold Cartesian product. Okay, so you see, we have the Pentagon equation, that is this equation written over here. We also have the reverse Pentagon equation, that is also this equation written over here. Okay, so these are the things, and let me say a few things where the Pentagon equation appears clearly as a Sederlin conformal field theory, also inside Poisson maps, and Lie Poisson maps actually by Zakrevsky. We can see in Hopf algebras in the regulation of piecewise linear three manifolds, in various combinatorics, and of course in discrete integrable systems. Solutions of this theoretical version of the Pentagon equation will be called Pentagon maps. This is what I'm going to speak about. And why I'm interested in Pentagon maps? Because again, some discrete integrable systems are naturally associated with Pentagon maps. For example, this Pentagon map that is given by, if I'm correct, by Doliva and Sergeev. Actually, yes, it is given by Doliva and Sergeev. It is related to the so-called normalization map, is related to the Hirota equation. Okay, so that is why we're interested into that.
Pavlos, can I ask something?
Yes.
Are they related via symmetries again?
No. Actually, you have to. I will show later how this is related. Not specifically this one, but how the Pentagon maps are related. Actually, you should take a specific composition of two Pentagon maps. Actually, a specific composition of Pentagon map and the reverse Pentagon map. And then, as soon as the compatibility condition is satisfied, then there is a proof by actually Kasaev and Sergeev that then this specific composition will be a Pentagon map, the tetrahedron map. So this is the way.
I see.
Yeah.
So thank you.
So it's a bit different. No, you're very welcome. Yeah. Okay. So the question then, a natural question is that, okay, what about lax matrices of Pentagon maps? or actually how one can see or actually answer this question if pentagon maps are equivalent to specific matrix factorization. And one question is what is, for instance, a lax matrix for this pentagon map that I showed earlier. This pentagon map N from the normalization. Okay, so this is what are natural questions that I try to answer. Well, I tried to answer in the recent work. And okay, and this will be the next part of this talk. But of course, first I will give a few more preliminaries. I will try to be quick with these preliminaries. And actually what I'm going to say now is that I have the map that acts on the Cartesian product. Now this of two sets, this set I will consider to be a division ring. And so actually in that respect, I will work in the non-commutative setting or the non-abelian setting if you like. And of course, because I will speak about maps, I will speak about actually equivalent classes of maps. And my equivalence relation is exactly this one that I have given here. So two maps will be considered equivalent if they satisfy this relation. And what I'm going to speak, everything will be well, actually all the symbols that will participate to the formulas of the map that I'm going to give, they will be non-commutative. But if you want to be more, let's say, well, to think it better, think it as division rings, for instance, quaternions or some other things. Okay, so this is what I'm going to speak, and I'm going to try to give via matrix refactorizations. I'm going to give solutions to the so-called N2-Anning or non-constant Yang-Baxter relation to the N2-Anning pentagon and reverse pentagon equation. What means N2-Anning or non-constant means that actually the three maps that participate on the associated Yang-Baxter or pentagon relations will be non-equivalent. Actually, this is what I'm going to call somehow N2-Anning solutions with N2-Anning Yang-Baxter and N2-Anning pentagon relation that I'm going to speak earlier. And just very quickly, just to state that how one can construct N2-Anning Yang-Baxter relations from given a Yang-Baxter map. So this is one proposition that if R is a Yang-Baxter map and T is a birational map, then this N2-Anning relation holds where the under braces specify the different maps. So you see here I have two different maps and R13 remains the same, the N2-Anning relation. Or if not all, and in the other case where now you have a symmetry phi of Yang-Baxter map, a symmetry is that when this a map phi is called symmetry, if this relation here has been satisfied, then I have two other choices to construct N2-Anning Yang-Baxter maps from a symmetry and a known Yang-Baxter map. Okay, the same thing can be extended to let's say, to the pentagon equation and to the reverse pentagon equation. And here is the setting. I mean, if I have a pentagon map S and two maps He and Psi, then this kind of relation here will specify well, N2-Anning pentagon maps. So let's say Chi 1 S1 2 is one map. Sigma 1 S23 Psi 3 is another map.
Pavlos, are they somehow, this is somehow related to something similar, the quadrillion, so how it's called, reflection maps?
Yes, boundaries.
Yeah.
Well, possibly, but I don't know exactly the connection, but possibly, but actually it was given in this paper by, well, I found it in a paper by Korepanov et al. Alive, and Dmitry, I think they call them boundaries, of course. This is why I use it now. I found it now, actually, it's called like that. I don't know exactly the connection, but I presume so. Yeah, I don't know how this could be.
Yeah, okay. Also, Talal has a question.
Is there some relation between N2-Anning pentagon? So, do you know what is the local pentagon equation?
Yes, the local pentagon equation is given by the work of actually Dimakis and Aristophanes Dimakis and Müller-Huijsen, and it's the tetragon equation. So tetragon equation can be considered as the local, well, from the local tetragon equation, you obtain pentagon equation. Okay, so from local pentagon equation,
Yes.
Well, if I remember correctly, you will obtain the next thing. It will be the hierarchy. It will be the, well, it's going to be hexagon. Yes, I think it's going to be hexagon equation.
So the hexagon equation is the good equation on the parameters for the local pentagon equation.
Yes, I think so. I think so. If I hope I don't say something wrong, but I think this is the case.
Thank you. Thank you.
Yeah. And this is really in the papers of Dimakis and
yeah, actually, I can comment on that. Paulos, you are right, because I tried the equations that Dimakis and Miller-Hoesen have on their paper, and I just make them local by considering matrices, and the indices are generalizations of the matrices, and it works actually. The local pentagon equation is the same as pentagon equation, but you just have matrices instead of maps and compositions. And it just generates literally solutions to the hexagon.
To the hexagon, okay, I see. Actually, yes, you are right about that. And actually, maybe, yes, in the paper of Dimakis and Miller-Hoesen, not the big paper, but there's another paper where they have an explicit, I think, hexagon map out of pentagon, local pentagon. But okay, we have to discuss it maybe, and yeah. But thanks, this is the case. Yeah. All right. And so now also I'm going to speak very quickly about this end-to-end examologic of equation that is actually a result from if you have a pentagon map, you can obtain solution to the homologic equation as well to the four simplex maps, four simplex equation. And that was actually proven by actually this construction to obtain solution of the homological equation and of the four simplex equation was given by Kassaev and Sergeev. And the construction is the following. It tells that if you have S and S bar to be pentagon, respectively diverse pentagon maps, as soon as this, what they call 10-term relation, is satisfied on the four-fold tensor Cartesian product, as is been written here, then this combination of reverse pentagon and pentagon maps is a solution to the homological equation. While this, let's say, combination of pentagon and reverse pentagon maps gives solutions to the four simplex equation. Okay, this is the interesting thing. But now let me, because I don't have so much time, very quickly, let me say on the construction, let me speak about the construction and how I can obtain we can obtain pentagon maps and actually Lax matrices for pentagon maps. So let's consider with IN the n times n identity matrix, and let me consider the sets pk and q lambda, where these are sets of some integers. And let me denote with Vj of x the n component row vectors written in that respect, and where this component of the vector will be considered as elements of the skew field. And now, having these things, I consider what I call matrices A, pk, and A, ql, q lambda, which are defined by substituting the lines lambda 1 to lambda k of the identity matrix with the vectors Vj that I had earlier. And similarly for q lambda. I'm going to give examples, of course, on how this works. Actually, what we obtain here, we obtain in that respect some certain type of matrices, square matrices, which act as a unique matrix on a subspace of half dimension of the dimension of the matrices. But I'm going to give examples about that and how these things work. And so when I have these matrices APK and AQ lambda, I have these refactorization problems that I write here. And I build these refactorization problems by having this, let's say, combination, this matrices APK and AQ lambda. Of course, yes, but I'm going to speak. I have many refactorization problems. Of course, some of them do have solutions, some others not. So now let me say more about the proposition. So now let me have the sets pk and q lambda, and let me fix to have the same cardinality. So kappa equals lambda. Let me see demanding the intersection to be the zero set, and let me set that k should be half the let's say the dimension of the matrix when n the dimension is even, or n minus 1 over 2 when n is odd. Then I can have a single factorization problem. This problem written here. It turns out to have a single refactorization problem, and by direct calculation, I can prove that this refactorization problem is equivalent to a birational pentagon map. While the refactorization problem from the transpose of this equation written above gives equivalent to a reverse pentagon map. Also, I have the following statements. Okay, clear the map PQ is a birational pentagon map. So actually specifying these sets P and Q, I have a pentagon map. The inverse map is equivalent to the following refactorization problem. And also I have the opposite pentagon map given by this refactorization problem. But because there is no much time, let me very quickly move to the examples. And let me speak first for the case where the matrices are 2 by 2. I have the matrix. In the matrix now I have P equals 1 and Q equals 2. This set, actually, I have the first set P and the second set Q. And the only choice I have here is to have A1 and A2, these matrices. I have a single factorization problem. And what it appears we have exactly one map. This is a map obtained from this factorization problem. This is a pentagon map. This is exactly the map that Doliva and Sergeev in 2011 introduced from geometric aspects, and they call it a normalization map. Okay, so this is the case in the 2 by 2 matrices. In the 3 by 3 matrices, I have more choices for these matrices. I have, let's say, these 6 choices given here. And well, I can have many refactorization problems. Now I have the refactorization problem of this proposition. And if I have this refactorization problem of this proposition introduced earlier, I have one pentagon map that is exactly like that. This is an extension of the normalization map introduced by by Doliva and Sergeev. And actually, this is a triangular extension if one is if one sees of the normalization map. Okay, so this is somehow the normalization map coupled with a linear map, triangularly coupled with a linear map. Okay, so this is a new result if you want. And furthermore, from these matrices, if I take this map, here is the nice in this notation that, well, in the superscript corresponds to the sets that I have chosen. I can have also Yang-Baxter maps, entwinning Yang-Baxter maps. But let me continue a bit more, because why it's interesting, why it is new these constructions. For example, if I now choose the set P to be the set with the number 1 and the set Q to have the numbers 2 and 3, so on and so forth, I have these 3 defactorization problems. Each one of these factorization problems corresponds to a map. The second one corresponds to a pentagon map. The first and the third, not to a pentagon map, but altogether they satisfy the entwinning pentagon relation. So actually we have an entwinning solution, entwinning pentagon maps through these cases. Okay, so here for the n equals 3, we can have classified all entwinning pentagon maps, but what I will be interested in the future is to try to see for arbitrary n the pentagon and the reverse pentagon maps, and clearly even for n equals 4, I have new entwinning maps appearing. Well, a new one actually. So it will be interesting to classify for n equals 4 higher. Also, it will be interesting to obtain entwinning homologic of maps via these constructions that I expect is not so difficult, and actually we can do it. And of course, I think that this constructive approach I showed here with this lax matrices with this matrix of this specific type might give us some hint on obtaining solutions to higher symmetrics and polygon equations. Okay, so that was it. I think I'm 3 minutes late, and thanks a lot for your attendance.
Okay, thank you very much.
Yes.
So are there any questions or remarks? Okay, question?
Pavlos, do you know such kind of equation as pentagon equation has a deep topological meaning? So it is used in combinatorial topological field theories. For example, it could be applied to construct invariants of triangulated 3 manifolds.
Okay.
Have you interested in this? And if yes, is your solution for the entwined pentagon equation is related with some interesting field theories?
Yes, well, of course, I'm interested in many things that the Pentagon is concerned, but I cannot answer this question. I don't know exactly how, and but I expect the running Pentagon maps to be related to something interesting. To tell you the truth, I do expect, but I don't know yet the answer how and how to do it. But it will be interesting actually. Yes, yes. And why it is interesting? Because as I showed, is somehow well, it's a new example of maybe it's the first example of end-to-end Pentagon maps. Yeah.
Okay, any more questions or remarks? Okay, Paulus, one more very final question. So,
Yes,
do you think that your symmetry method from your paper with Matse, Tassos, and Papageorgiou for going from 3D lattice equations to tetrahedron maps and the other way around, do you think it may work for Pentagon maps?
Okay, this is also a good question as the previous one, but again, yes, I don't know the answer again. I mean, maybe
it's not very obvious as I don't know. I mean, geometrically, for instance. I mean, it's not obvious is not a good question, but it's not very natural.
No, it's a good question because somehow you see.
I mean, it's not a good word. Obvious. I meant natural is not as natural as probably for.
Yes, because somehow due to the fact that, for instance, the AKP map, the Hirota map, decomposes to the product of a pentagon reverse pentagon map. Well, it should be somehow something can be obtained from the symmetry reduction, but I don't know exactly what. I mean, maybe one has to use, well, not really symmetries, invariance of the symmetries to have this pentagon map. He has to use something else and rewrite the Hirota map into some, I don't know, semi-invariance of symmetries or, well, actually not even invariance. But maybe it can be done. But I don't know. I don't know how to do it yet. But it will be interesting to try it.
Yeah, okay, I think it will be very interesting. Anyway, okay, Pavel, thanks very much again.
Thanks a lot.
So the next speaker is Sergei Sokolov from MIPT, and he will be talking about a reduction in a vortex system with symmetry. Пожалуйста.
Я думаю, что просто надо сфокусировать.
Кликнуть один раз, да.
Вот эта штука работает. О, все заработало.
Да, я буду менять.
Давай я буду.
Кстати, это она wireless, так что можно.
Да. Отлично.
Подожди.
с вихри. Thank you, thank you for organizing this. Have a talk on this conference. I'm always great, big pleasure stay in Yaroslavl, and it's the next time. Now I want to speak about some vortex structure and a responsible mathematical problem. And I want to demonstrate how we can use the symmetry of this system to reduce the differential equation of finite dimensions to a more small order. And the symmetry not so easy to exhibit for us as more deeply because we have some topological effect like degenerated bifurcation, because it's not so easy to observe this effect without the a priori information about symmetry in this system. We have some special type of bifurcation is the 3 tori to 1. Now we can start. I have a lot of time, and that is my main reason, because I skipped some large references in this area. Is the classical Helmholtz, Kirchhoff, Hrebly, Poincaré, RF, and Valery Vasilievich Kozlov classical papers about this problem. The classical papers starting to study vortex structure in unbounded liquid. The first of all is the perfect liquid without viscosity. And many times we think about the system like a theoretical interest. But starting the 2000 and more later, we have a lot of examples like perfect liquids go to experimental physics observed, and this is the first of all Bose-Einstein condensates observed in the so-called low-dimensional physical systems like graphene layers, B layers, multi-layers of graphene, starting from the papers of Alexander Fetter and Grotchek, Murray, Kuropati. We have some so-called cold atoms, the correlated systems with spin without the principle of Heisenberg, and condensate on the same level of the energy, and we have observed one of the first example of the experimental data to Bose-Einstein condensate. It should be noted that all well-known super viscosity, superfluidity, superconductivity, and so on effects in the physics and condensed matter and perfect fluid dynamics, well known maybe on 1910 after Kamerlingh-Onnes and so on. This is the such effect as correlated systems, Bose-Einstein condensates. And now we can start the formulating our problem, setting up. And I recall to dear colleagues, what does it mean, the vortex filament, and what kind of motions we can observe in this system. First of all, we can try to solve the equation in partial derivatives, describe the perfect fluid. And the first of this solution is the harmonic function. And if we can simple connected manifolds, the area in which we can try to solve this equation, we doesn't have such like a vortex filament, like a point vortex solution. And if we can try to observe this one special motion of our perfect fluid, we have a unique solution. This name, the vortex filament, or if we reduce to the 2D problem, we have a point vortex. It's very simple system, and we can try to solve the problem with some quantity of these vortex filaments. It can be done by many ways. One of these is the Kirchhoff solutions and Lin solutions, where the differential equations of motion can be represented in Hamiltonian form. But we can now discuss more easy to go to this area with the simple geometric way. We have put in flow which induced the single vortex on the distance r from its core. We put another one vortex filament, and velocity of motion of the first vortex is the speed of flow induced by a second vortex in this point. After that, we repeat this procedure and add and one filaments, and we can try to solve the problems of n vortex on unbounded perfect fluid. It's well known we have only exact solution, integrable case only for the one filaments, with two filaments and three filaments. Three filaments is the maximum of integrability. It was proved by Walter Gröbli, was PhD student of Kirchhoff in his thesis. Now we go to the Bose-Einstein condensate because the system more simple with respect to the classical perfect fluid, because more simple Hamiltonian describe the system presented in the physical papers, and we can try to see how behave this system from topological point of view, what kind of bifurcation we can observe in this system, and so on. And we can introduce some simple equations of motion. Our dynamical variables now we can define the x and y, that's coordinate of our point vortex, and his left hand side, the velocities of these vortices, we can find the simple sum of the velocities induced of another one vortex in the point x and y with index k. And after that, we can represent these equations in more comfortable for us Hamiltonian form. And now, from this point, we only see the system of 2-point vortices. But we can restrict this problem, more strong problem. We have a more strong problem. The 2-point filament, 2-point vortex or 2-vortex filament inside the circle cylinder area, or maybe from the Bose-Einstein condensate, so-called harmonic and some harmonic potential. Huh? Oh, in harmonic trap, yes. Thank you. In this case, we have a more comfortable the Poisson structure, like in our Kirchhoff case, the phase space of the such system. This is the direct product of two disk minus set, which means the diagonal of this direct product, because we don't show what behave we have when the coordinates of 2-point vortices coincide. We not discuss the collisions. And in this case, we have one symmetry, because this system has symmetry by rotation group, and due to this symmetry, we have additional first integral, momentum of vorticity, F capital, which depends only on distance from the origin point to our point vortex. After that, we introduced so-called two-parametric family of integrable Hamiltonians, this one with the second integral, which described all cases presented in physical reviews and physical papers, where the physical parameter B is the constant number from 1 to maybe 10, which described the derivative of our harmonic potential and can be introduced maybe in situ. And we introduced, let us define the momentum mapping. This is so mapping that to each point of our phase space map to two-dimensional spaces where the constant of our first integrals is coordinate in this space. And denote by C all critical points of the momentum mapping. Does it mean in which rank of this mapping less than maximal, less than 2. And critical values set, sigma, is the image of our critical points called bifurcation diagram. This way we can explicit determine the bifurcation diagram in analytical way by definition the invariant submanifolds of our phase space, by introduce some polynomial with respect to our x and y coordinates, our point vortices, and this theorem about the critical set of our and invariant manifolds of our Hamiltonian system with 2 degrees of freedom. Now we goes to polar coordinates and we can do critical subsystems corresponding to theta 1 equal to theta 2 and equal 1 minus theta 2 equal to pi. This corresponds to the special position of our vortices is representing of these critical sets take us the two bifurcation diagram curves. One of these is the such one, and another one, P2, is the pi 2 is the another one, and this take us determine the motions of these critical points corresponding to points of bifurcation diagram, and this is the explicit form of these periodic motions. The first one, gamma 1, is the motions corresponding to points pi 1, and the gamma 2 corresponds to pi 2. After that, there's no matter, is the eigenvalues of our linearization symplectic operator take us the solution of stability problem for the critical points, because our curves, bifurcation curves corresponding to points and the pre-image of momentum mapping corresponding to stable motions and unstable motions. It's not so easy to know. And after that, we can define some bifurcations of Liouville-Torai. This some areas in bifurcation diagram. We can see one of our bifurcation diagram points have a blue color and another one red color. Inside this area, which has named area of available motions, outside of this we have a zero set because we have no any motions. Inside the gray points we have one torus, and inside the more dark gray color we have points corresponding in the pre-image of momentum mapping have two different tori. And with this arrow we define the type of bifurcations which can be defined due to Mikhail Pavlovich Kharlamov definitions by this one. Alpha is the bifurcations from 0 point from the critical S1 to one two-dimensional tori. Beta is the unstable bifurcations. That means one tori transition to this one as the figure 8 direct product on S1 to S1 to two tori, and the gamma is the stable bifurcations, two tori to one two-dimensional tori to torus to two tori due to the burn the second tori from the critical circle S1. And after that, now I can more quickly to define some trick with the reduction, because it's well-known data. Okay. And this is the bifurcation diagram in the one special case where doesn't exist the points inside the red curve. The blue curve doesn't exist. Is the special case. And if you try to interesting about what does it mean the points of this on this curve, we have rotate inside this circle cylinder 2-point filaments on the distance R1 and R2 placed on the one diameter but not equal distance. This point, when the Q1 equal to Q2, we have the distance R1 equal to R2, and the second one is the change the distance, change the sign of inequality. And after that, we go to another one bifurcation diagram, not so simple like when we have a vortex with the different signs, opposite signs. We starting to explain what does it mean bifurcation diagram in the case when we have intensities of our vortices, and does it mean the parameter A in the two-parameter family of integrable Hamiltonian more than 0. What does it mean in this one? We have a more interesting bifurcation diagram in this case. If you try to take your interesting in this point, it seems like two cuspidal points coincide in this point. It's not so simple to explain what does it mean coincide, because we have two curves, two bifurcation curves, the red one and the blue one, and in this critical case, critical, not so in the previous and the previous sense. No. Yes. In the previous sense, because critical with respect to bifurcation diagram. This is the bifurcation of bifurcation diagram, where when our parameter, bifurcation parameter, change through the critical value, we have coincide this cuspidal point with the point of tangency of this blue curve. In this case, we have some additional symmetry. And this is the main theme of my talk today. In this case, we have, I skipped some slide. We have additional condition, A equal to 1, because now we have identity vortices, the same direct of rotation of our fluid, and coincide the values of these intensities, and this does it mean A equal to 1. In this one, our critical sets N1 and N2 have a simple form, because this is the set of the solution of the simple system of equations. And we can introduce some addition change of variables that means that we can release some addition symmetry in our explicit expressions of our critical subsystems, and this is the parameterization, not so simple with the square root, but not so huge, because if we have no symmetry, only implicit values, implicit defined sets. We have only implicit defined function. And now with the explicit expressions, and this take us the another time has the explicit expressions for our bifurcation diagram curves, and another one, the change of variables. This picture demonstrate coinciding the tangency point with the cuspidal point, the second cuspidal point. And after that, we have introduced some special variables what have a sense, have a geometric sense. The next one, we can find the center of vorticity for these two symmetric system of two vortices, place the origin point of the rotation system of frame of reference in this point, in the center of vorticity. One of the axes of this rotation system contains the one vortex, and another one vortex have coordinates x2, and y2 with respect to this rotation frame of references. In these variables, our system, Hamiltonian system, reduced to the three variables separating from which to another, U and V, then the special coordinates means the relative position second vortex with respect to the first, and alpha is the angle of rotation of this coordinate, in these coordinates. And after that, our Hamiltonian system with the reduced Hamiltonian doesn't contain alpha. We have only the first order, with 1 degree of freedom system. Critical values of H1 immediately take us the one component of the two-dimensional tori bundled, no, trivial bundle. I now to show you the picture. In these coordinates, we have explicit representation of the very seldom, very rare bifurcations. This is the one torus from 3 tori. You have 3 tori. This picture can be direct product by S1, of course. This is the reduced system, and if you direct product by S1, you can see 3 tori. S1 direct to S1, 1 tori, and so on. The critical layer of the Lagrangian bundle, we have this topological curve, this union S1 with 2 points, and this is a single layer, unstable single layer, and after increase bifurcation parameter, we can see this in these points our curve have no intersection, and this single layer goes to the simple diffeomorphic to S1. And after that, by product, direct product on S1, you can see single tori. And this is another one representation of this fact. This is the critical levels of reduced Hamiltonian H1 for the case A equal to 1 and B, another one bifurcation parameter more than 3. And after that, you can see the absolute dynamics project on R3. We can equal y2 to the constant value, and now we have see the windings of our two-dimensional tori by our trajectories of our Hamiltonian system. Now I will stop, and thank you for listening.
Thank you very much. Any questions or remarks?
Yeah, is it possible maybe slightly deform Hamiltonian functions that such a model could be integrable? Could be integrable.
This is integrable. This all of cases is integrable. No. This the two vortex filament inside the circular cylinder, we have a two-parameter integrable Hamiltonian system. Thank you.
Any more questions or remarks? Okay, let's thank the speaker again. Thank you very much. So the next speaker is Maria Nifurenko from Moscow State University. So the slides will be in English, but however, she will be speaking in Russian. Just a second. Пожалуйста.
Слышно? Ага, отлично. Значит, сегодня я хочу рассказать про структурно устойчивые вырожденные особенности интегрируемых систем. Так, видимо. Сработало. Нет, все-таки. Да. Механики и симметрической геометрии мы хотели бы классифицировать орбиты к рангу 1 типичных интегрируемых систем. У нас будет k плюс 1 степень свободы. И исследовать их структурную устойчивость. Первую задачу можно свести на самом деле к задаче теории особенностей, то есть просто классифицируем G-инвариантные функции с двумя переменными и с k-параметрами. У нас действует группа поворотов, собственно, можно считать, что просто группа ZS. Здесь мы решаем первые проблемы, то есть классификацию гамильтоновых систем, интегрируемых гамильтоновых систем для параметров меньше 3. Этот случай был уже известен для одного параметра в работе Калашникова и для параметров 1 и 2 для группы для группы порядка меньше 3. В работах, которые я сейчас покажу, значит, да, сначала скажу, что на самом деле тот результат, про который я говорила, про классификацию функций, есть уже более общая теорема, моя и моего научного руководителя Елены Кудрявцевой. Мы классифицировали функции всех типов k, то есть вот тот параметр k, который мы говорили, что это число параметров, мы дальше будем говорить, что это тип. И для порядка группы больше 2. Да, и, собственно, доказали приводимость семейства гладких функций. Скажем так, нашли все версальные деформации этих функций, которые мы исследовали. Для группы порядка 1 и 2 результат уже был известен, собственно, в работе Елены Кудрявцевой. Еще была классификация Вассермана 1988 года, но он классифицировал не по числу параметров, то есть не по числу k, а по кратности Милнера. Дальше, как обычно, мы рассматриваем интегрируемые системы. Возникает лагранжевое действие. Соответственно, в слоях у нас получаются Тор или Леувилля. И мы хотим изучать структурную устойчивость. Значит, введем определение стандартной модели. Стандартная модель будем называть интегрируемую систему со стандартной моделью, если она задается следующими формулами. Да, значит, у нас многообразие следующего вида. Мы факторизуем по группе G. Группу G определяла ранее, это повороты. Вот у нас такая симметрическая форма. И следующее семейство функций, где функции h будут определены далее. Сейчас. Собственно, вот этот набор функций. То есть у нас всего 2 параметра, поэтому образуется 2 семейства. И как здесь видно, у нас порядок группы любой. И при порядке группы больше, чем 4, у нас получается вот такая серия. Собственно, видно, что, сразу скажу, что одни из самых сложных случаев, это где возникают параметры, в теории особенностей говорят модули. Это, то есть, случаи s равно 4 при одном параметре, s равно 6 при 2 параметрах и s больше, чем 6. Собственно, поэтому вот эта серия случаев не исследована пока, то есть нет бифуркационных диаграмм и фазовых портретов. А вот здесь уже доказана структурная устойчивость. Собственно, сама теорема. Если мы рассматриваем 4-мерное и 6-мерное многообразие, рассматриваем класс систем полуторических, то есть функции f2, fn образуют n-1-мерное действие Тора, и класс стандартных систем, то есть все особенности которых дифеоморфны стандартным, послойно дифеоморфны стандартным, мы будем называть классом стандартных интегрируемых систем. И если, да, собственно, этот класс открыт и плотен в классе полуторических систем, если у стандартной модели есть модуль но при этом фазовый портрет от него не зависит, то тогда тогда особенность будет гладко структурно устойчивой. А если мы возьмем этот параметр, который в некоторых системах возникает, и при малом шевелении портрет изменяется не сильно, тогда будет просто структурная устойчивость. Да, собственно, при n равно 2 уже было исследовано, это параболические траектории в работе Калашникова, и для n равно 3 он получил их бифуркации. Собственно, вот представлены гамильтонианы. Их явный вид получился с помощью теоремы о классификации функций из теории особенностей. Это тоже наш результат с Леной Кудрявцевой. Часть из них уже была известна, но не была проведена именно классификация. Было доказано в одну сторону, что если у нас есть вот некие условия, мы получаем эту функцию. Мы, собственно, доказали критерий. Далее, собственно, результаты, которые были в прошлом, бифуркационные диаграммы и фазовые портреты. При k равно 1 это результат Калашникова. Собственно, он их все получил, то есть и диаграмму, и фазовые портреты. Вот. Собственно, это известные случаи все. Слоение Льювиля. Далее при k равно 2, то есть когда у нас число параметров уже равно 2, при s равно 1 это результат Льва Лермана. Он тоже получил бифуркационную диаграмму и фазовые портреты, и таким образом доказал структурную устойчивость. Кстати, при k равно 1 все наши особенности структурно устойчивы. При s равно 2 тоже это результат Льва Лермана. Дальше при s равно 3 в случае k равно 2 он не возникает. Возникает сразу 4-й случай, и это результат Владислава Кипкала и Елены Кудрявцевой. Единственное, что было сделано пока, сделаны бифуркационные диаграммы, но нет фазовых портретов, то есть не доказана на самом деле структурная устойчивость. И что осталось, какая задача? Для s больше 4 изобразить бифуркационные диаграммы, фазовые портреты, проверить зависимость от модуля, то есть от этого параметра который вот возникал в семействах. И таким образом мы докажем структурную устойчивость. При s равном 4, собственно, осталось ее доказать. Бифуркационная диаграмма уже построена. Собственно, на чем была основана теорема результат? Это теорема теории особенностей, классификация G-инвариантных функций, G-инвариантных ростков. Собственно, мы рассматриваем алгебру G-инвариантных функций, гладких G-инвариантных функций, с числом параметров именно в этой теореме меньше 3. И тогда, если мы берем некий росток из этой алгебры, то он эквивалентен для каждого порядка функций, для каждого числа параметров, приведенному здесь семейству. И в обратную сторону, собственно, это единственное. Мы описали все классы таких особенностей в этой алгебре. Ну, наверное, это пропущу, это уже пошло доказательство. Давайте сразу расскажу про обзор, именно связанный с теорией особенностей. Значит, при k равно нулю, это морсовский случай, это было доказано в работе Арнольда. То есть, напоминаю, мы рассматриваем только G-инвариантные функции. Вот, собственно, при k равно нулю, то есть, когда число параметров 0, у нас возникает морсовский случай, это было доказано в работе Арнольда. При k равно единице, не знаю, видно или нет это. Да, собственно, не знаю, насколько это понятно, на диаграмме по горизонтали порядок группы, по вертикали число k. Это либо тип, либо число параметров, ну, собственно, число интегралов в нашей системе. По горизонтали было доказано Калашниковым. Он не занимался теорией особенностей, он занимался как раз классификацией гамильтоновых систем. И таким образом получил классификацию гамильтонианов, но и тем самым функций. При порядке группы 2 это результат Кудрявцева и Лакштанова, а далее здесь секторы, это, собственно, классификационная теорема, которая будет дальше. Значит, желтый сектор, это было уже в нашей статье с Еленой Кудрявцевой и моей. Эта статья только про классификацию функций, а не про гамильтоновые системы. И вот недавно нам удалось доказать зеленый сектор и синий, то есть для всех случаев K и S. Ну, эта таблица чисто техническая, потому что при классификации возникает очень важный параметр – число Милнера. И, собственно, здесь написана связь числа Милнера, числа модулей, то есть вот тех… Вот здесь вот видно тех вот параметров А. То есть вот у нас есть параметры как интегралы, ν1, ν2, а есть еще один тип параметров А. Это называется модули. И из-за них возникает как раз проблема и с фазовыми портретами, и, собственно, с классификациями, потому что возникают несколько случаев, и одним методом они не решаются. Поэтому, собственно, доказательство проводилось вот в несколько секторов таких. Это просто техническая таблица. Здесь представлена связь и условия на коэффициенты. Вот. И, ну, собственно, сама теорема, которая говорит, что если у нас есть, ну, действует конечная группа с порядком S, и мы берем гладкую функцию из алгебры G-инвариантных гладких функций, то ее особенность имеет тип K, тогда только тогда, когда мы можем нашу эту функцию привести к некоторой нормальной форме, скажем так, и примеры нормальных форм я уже показывала. Собственно, все.
Есть вопросы или замечания? Пожалуйста.
Простите, пожалуйста, на последнем слайде перед литературой у вас был порядок группы. Нет,
Да.
еще дальше. Еще дальше. Можете пояснить, что такое порядок группы G?
Смотрите, у нас действует группа поворотов, конечная группа. Можно сказать, что мы рассматриваем просто группу ZS, то есть группу остатков. Ну, вот это S будет порядком группы. Да. Да.
Маша, я вот эту деятельность ничего не знаю, поэтому у меня вопрос такой вот просто по названию вашего доклада. Видите, вот вы пишете «стабильные вырожденные особенности интегрируемых систем». Интегрируемые системы…
Да.
Вот, теперь второй вопрос в продолжении. Значит, что такое стабильное, я хочу понять, что такое вырожденные особенности, и правильно ли я понимаю, что речь идет про глобальные решения? Ну, например, замкнутые траектории. Нет?
Глобальных случаев там, как я понимаю, нет. По поводу... может быть, я неправильно поняла. Да, конечно. Я думала, вы имеете в виду про глобальность, там, связанную с критическими точками, которые возникают к вопросу о вырожденности. Давайте на каком-нибудь примере посмотрим. Ну, скажем, самый простой какой-нибудь. Но у нас есть интегрируемая система, то есть есть некий набор интегралов. Ну, да, то есть у нас есть набор функций, которые находятся в инволюции. Да, правильно. На них Сейчас, секунду. Ну, мы рассматриваем стандартные модели, кроме того. То есть у нас... Но стандартная модель определяется вот следующим образом. У нас есть конкретное многообразие, конкретная форма. Это просто стандартно, чтобы так обозначать. Форма. Симплектическая. Невырожденная. F — это вот семейство функций, там гамильтонианы, интегралы. Да. Стоп, секунду. Да, все верно. Да. Да. Дальше мы берем класс стандартных интегрируемых систем. Это... Да, конечно. Ну, значит, извините, я, видимо, что-то не так поняла. Да, извините. Мы рассматриваем особенности в слоях. То есть в каждом слое у нас система должна быть... Да. Да. Угу. Да. Если честно, простите за невежество, не могу так сразу сказать сходу. Нет. Да. получается, что да. Да, да. А что вы имеете в виду, извините, под интегрируемыми геодезическими потоками? Прям вот. Хорошо, да, спасибо, да. Спасибо. Собственно, все.
Хорошо, тогда еще раз благодарим. Спасибо. Хочу сказать, что доклада Александра Орлова не будет, он не сможет сделать доклад. Так что последний докладчик сегодня это Сергей Гонин. Сергей, ты с нами? Онлайн, да. Сергей, ты с нами? Okay, Sergey, now we can hear you. Try to share your slides, please.
Yes. One moment.
Just we'll move it there. Okay, Sergey, you can see your screen now.
Yes.
Okay, you can start whenever you're ready.
Yes. Okay, I start. First of all, I would like to thank the organizers for the opportunity to give this talk. As you can see in the title, I will speak about algebraic constructions of Miura-type transformations for differential difference equations and associated new integrable equations. Let me first introduce the main notions and notation. We study differential difference equations of the following type. Here, u is a vector function of two variables, an integer variable n and a real or complex variable t. Ut is the derivative of u with respect to t, and for any integer I, ui is the so-called shift of u. So ui is another function of s of n and t given by this formula. So ui is this function for fixed I. Ui is this function of s of n and t. And here on the left hand side we have ut, and on the right hand side a function capital F of several variables of the functions u alpha and so on u beta. And this equation 1 must be valid for all n. For every, which means that it is equivalent to an infinite sequence of differential equations. Here you can see it. For every n, we have a differential equation. Now, what are Miura type transformations? We consider another differential difference equation of similar type for a function for a vector function v, and suppose that we have a transformation given by formula 3. Here it says the following: if a function v satisfies equation 2, then u given by formula 3 satisfies equation 1. Then such a transformation from equation 2 to equation 1 is called a Miura type transformation. A simple and well-known example is the following. Consider the Volterra equation. Here u and v are scalar functions in this example. Consider the Volterra equation and the modified Volterra equation, and the Miura type transformation is this simple formula. Now let me say a few words about importance of Miura type transformations. They play an essential role in the theory of integrable nonlinear partial differential and difference equations. So here today I speak about Miura type transformations for differential difference equations, but similarly one can define them for partial differential and difference equations. Excuse me. And they have such transformations have many applications, and in particular, the following happens when one tries to classify a certain class of integrable equations. One often finds a few basic equations, such that all other equations from the considered class can be obtained from the basic ones by means of Miura type transformations. Examples of such results can be found in the listed works. Also, it is well known that conservation laws and auto-Backlund transformations can often be constructed by means of Miura type transformations. Hence, it is desirable to develop systematic methods for constructing Miura type transformations. Now, the main ideas of my talk. There is already one publication in 2016 with George Berkeley, and my talk extends the results of this publication. I will recall some results of it and add something new. So the main result is a method to construct Miura type transformations for differential difference equations using gauge transformations and invariance of some group actions associated with Lex pairs of such equations. And in the method, one step of the method involves simplification of a Lex pair by gauge transformations. And this can be regarded as an independent result. So we show how one can simplify a Lex pair by gauge transformations in many cases. The method is quite widely applicable. You see, I have here a list of equations where the method has been successfully applied. You see, well, quite many different equations. And what we get applying applying the method to a known Lex pair of some known equation, we get in general many new Mura type transformations and new integrable equations related to this known equation. And it is
Sergey, all the equations you have in the list are differential difference, right?
Equations. Yes, sure, yes. But a similar approach with some modifications works also for difference equations, but today I will not speak about this.
Okay, thank you.
Okay, and it is important to mention that some steps of the method generalize a result of Drinfeld and Sokolov on Mura type transformations for the partial differential KdV equation. So let me introduce a few more notions and notation. Consider again our differential difference equation. An important ingredient is the so-called shift operator, which replaces n by n plus 1 and ui by ui plus 1. Now, what is a Lex pair for such a differential difference equation? We have two matrix functions, m and u, which may depend on ui and a finite number of the variables ui and a complex parameter lambda, and consider the following equation 7. So we assume that the matrix M is invertible, and equation 7 holds as a consequence of the initial differential difference equation. Then the pair MU is called a Lex pair for equation 6. We abbreviate it as LP. And what is the meaning of equation 7? It basically says that the following auxiliary linear system is compatible modulo equation 6, where psi is an invertible d times d matrix function.
So yeah, am I right so that you start in principle from an integrable PD that have AKNS yes, type of Lex pair, and M is a Darboux transformation, right?
So what you say is a source of examples of Lex pairs for such differential difference equations, but
not necessarily all of them.
Not all Lex pairs are constructed in this way. I
understand, and moreover, I am talking only about integral PDs that have particular type of Lex pair of AKNS type, where the differential operator is separated from the. Anyway, okay, sorry, I understand what you mean. Okay.
Okay, so the notion of Lex pair is quite general. Many Lex pairs come from Darboux transformations, but not all of them. Okay, now gauge transformations. G is an invertible matrix function, and formulas 9. So if we have a Lex pair MU, then formulas 9 give us a new Lex pair, which is called gauge equivalent to the initial Lex pair with respect to the gauge transformation G.
Сергей, а я прошу прощения, вот матрица M, она может быть линейная или она обязана быть линейной по спектральному параметру лямбда?
M can depend can be any, in general, any matrix function. In examples, it is rational. The dependence on lambda is rational in the considered examples, not linear, but rational. But in general, it can be elliptic or anything. So the dependence on lambda can, in general, be arbitrary.
No, for the most popular example is, I guess, the derivative NLS of an Alain-Newell. It's only, there's no linear matrix M. It's square, lambda square. But in general,
but
yes, he's right.
It can also be elliptic. So in principle,
Frank Neff,
rational or elliptic. And possibly curves of high genus lambda can be in principle any dependence on lambda is allowed. Now an outline of the method. So again, so more details on the notation. Our function u is a vector function with capital N components. We have the differential difference equation, and so UL is equal to SL applied to U. So SL is the else power of the shift operator. This is the component of it, so of the function UL. And it is important to remember that U0 is just U. Now now UIL are regarded as independent quantities, sometimes called dynamical variables. So we will consider functions of the variables UIL. Right. Okay, now the first step of the method is to simplify the lex pair. And the first simplification is very easy. We are allowed to make a relabeling in this way. So UI U1, well, we have in the components of our function U, we can make shifts in principle. So this relabeling is an invertible change of variables, an obvious change of variables, but sometimes it simplifies things. And in particular, after a suitable relabeling of this type, we can assume that our function M depends on U and non-negative shifts of U. So it is important that here we have U0, U1, and so on up to UK, where K is a non-negative integer. So no negative shifts appear in M.
All these are shifts, correct?
Yes, yeah, the lower index determines shifts.
Yeah, so 0 is just without shift.
Sorry?
The 0 is just no shift.
Right. 0 is 0 shift, which means no shift. This is an obvious step. If initially we have some negative shifts, then after relabeling, we can get rid of negative shifts and consider only non-negative shifts and get only non-negative shifts in M. So this step is obvious. Now, next step is more interesting. It is the following. Suppose that we have a lex pair where M depends on non-negative shifts of U. Now we try to simplify M by gauge transformations, and using gauge transformations, we try to get rid of positive shifts. So we try to find a gauge transformation such that the corresponding gauge equivalent M hat depends only on U. You see, we try to get rid of positive shifts in M. And there is a criterion on when this can be done, which is theorem 1. So consider a matrix function depending on non-negative shifts, and suppose that this matrix function satisfies the listed conditions, then there is a gauge transformation such that applying this gauge transformation, we get rid of the of UK. So applying this gauge transformation, we get rid of the of the highest shift. we get rid of the dependence on UK. After this gauge transformation, we have already shifts up to k-1. Then one can get one can check again the same conditions for k-1, and if the conditions are satisfied, then one can get rid of UK-1 and so on. And it turns out that this works quite often for many Lex pairs. Many Lex pairs can be simplified in this way. We get rid of all positive shifts in them. And a simple example. Here, initially, we have a 0 shift and 1 shift. After a gauge transformation, we get only 0 shift. And okay, so this is, and actually the inverse statement is also true. So if we can get rid of UK, then this means that M does satisfy those conditions. So actually, theorem 1 is if and only if, actually. Okay. And now step 3, this quite technical. Now we suppose that we have a Lex pair which where M depends on U and lambda only, so only 0 shift and lambda. Now we, using such a Lex pair, we construct Miura type transformations using invariants of some group actions associated with such a Lex pair. The construction is quite technical, and the details, well, I have in principle a lot of details written here, and I can send you the slides if you wish. Also, even more details can be found in the published paper. So theorem 1 is not published yet, but step 3 is published already in that paper, and also I can send you the slides. But let me briefly overview what is written here. For a given Lex pair of where M depends only on U and lambda, first of all, we with such a Lex pair, we associate a sequence of groups H0, H1, H2, and so on. The groups HP are defined by induction on P, and the definition is written here. These groups consist of certain invertible D times D matrix functions of lambda. Okay. Next ingredient is a Lie group associated with the Lex pair, and we do the following. We consider the algebra of polynomials in lambda and its quotient modulo the polynomial lambda minus c to the power k, and consider invertible matrices with entries from this quotient algebra. So the elements of such matrices can be described as sums of this type, and it's the set of such matrix functions is a Lie group. So we work modulo the relation lambda minus c. C is a fixed constant. We work modulo the relation lambda minus c to the power k is equal to 0. Now we introduce coordinates on this Lie group, W, K, Q, I, J, denote the whole group by G. Now next steps are the following. Our elements of our groups HP act on the group G by left multiplication, and in the way use the relation lambda to the power c minus lambda. Well, this relation we use, and so when we meet a function of lambda, we take its Taylor series expansion and truncate the Taylor series as the term lambda minus c to the power k minus 1. Okay, so we have HP left invariant functions. Also, for any subgroup H, we have H right invariant functions. Okay, now suppose that those W's are functions of Sn of n and t. Consider our auxiliary linear system and substitute in place of psi, we substitute such a sum modulo our relation. Then it's easy to understand that this system of equations gives equations of gives a number of scalar equations for small w's. Again, we use truncated Taylor series. Okay, now we consider functions on G, and we know how to apply the shift operator to them. Since we know how to apply the shift operator to coordinates on G, and theorem 2 and theorem 3, well, so why did we introduce those groups HP? The answer is the following. If a function z is HP left invariant, then these shifts of it do not depend on UL. This follows from the definition of the group HP and the property of Z to be HP left invariant. And furthermore, if H is in any subgroup and Z is H right invariant and at the same time HP left invariant, then those functions are H right invariant. And theorem 3 is, well, it is the result, for simplicity in theorem 3 here, I consider the case of scalar equations, so the number of components is equal to 1, but in the paper, the case of arbitrary capital N is considered. So the main idea is the following. We consider our group G and suppose that we can choose a subgroup H of codimension R and a function Z on G such that Z is H right invariant and is left invariant with respect to this group, and also it satisfies certain non-degeneracy conditions which are written in the paper. Then we introduce this notation, okay, and recall that we have those equations 11. You see equations 11. So small w's use are in coordinates on our group G. We know how to apply the shift operator and the derivative with respect to t to those coordinates. And it turns out that, and now function z is a function of those coordinates small w. And it turns out that if z satisfies those conditions, then we can express everything nicely such that we get a Miura type transformation. So for arbitrary function z, this is not possible, but if z satisfies the conditions, the assumptions written here, then using those equations 11, one get a Miura type transformation of this form. So this is the case of scalar equations. But a similar construction can be done for n-component equations with arbitrary capital N. And moreover, so in we had the group G described here for simplicity was this group. depending on DCK, but one can in principle consider a more general group which is equal to the product of several groups of this type. This is also written in the paper. And I conclude by showing two examples very briefly. A new Miura type transformation for the Narita-Ito-Pogayevlensky differential difference equation. This is the Narita-Ito-Pogayevlensky equation. This is the Miura transformation, and this is a new integrable equation which is related to the initial equation by Miura type transformation. And another example, consider the modified Narita-Ito-Pogayevlensky equation of order 2. And so here a Miura type transformation for it, and this is a new modified, so this is a new differential difference equation related to the initial equation by Miura type transformation. That's all. Thank you for your attention.
Okay, thank you very much. Any questions or remarks? One question.
Сергей, у меня два вопроса. Значит, вот первый пример, который меня бы очень сильно интересовал в вашем докладе, но я его не увидел. Вы упоминали цепочку Адлера-Постникова. Правильно я понимаю, для нее вы построили преобразование Миуры, и эта цепочка у вас модифицированная выписана где-то?
Да.
А посмотреть на нее в вашем докладе сейчас нельзя?
В докладе нельзя, в статье. Давайте я текст статьи, у меня текст статьи вот под рукой, давайте покажу текст в тексте статьи.
Хорошо.
Значит, у Адлера-Постникова много вообще построено уравнений. Давайте я один из примеров покажу.
Давайте.
Сейчас.
Да, это вряд ли.
Вот, значит, Адлер-Постников, у нас тут целая секция про Адлера-Постникова.
Это опубликованная, да, работа?
Да. Значит, вот мы пару Лакса пишем. Ага, значит, значит, итак, исходное уравнение Адлера-Постникова это 195, это значит вот уравнение Адлера-Постникова, да, 195 и 196 это уравнение Адлера-Постникова.
Угу.
А сейчас, значит, какие мы построили Миуры для него. Вот, значит, да, вот 205, это случай двухкомпонентной системы.
Да,
здесь.
понятно. Угу.
Значит, 205 это Миура, и вот, значит, написано 205, а 206 это модифицированное уравнение. И, значит, 205 является Миурой из 206 в 195.
Да, понятно. Хорошо, и второй вопрос. Сергей, последний вопрос. А ваша процедура, она позволяет двигаться дальше? То есть, например, построить дважды модифицированный, трижды модифицированный, если они существуют?
Да, именно. Значит, смотрите, делается следующее. Смотрите, значит, у нас есть исходное уравнение с парой Лакса. Значит, мы построили Миуру и модифицированное уравнение. Дальше мы, как вы знаете, можно поднять пару Лакса на модифицированное уравнение. Так? Максим?
Да, дальше. Просто у него микрофона нет.
Значит, можно поднять пару Лакса на модифицированное уравнение, но на модифицированном уравнении поднятая пара Лакса, там в функции m будут как раз положительные positive shifts будут. И вот как раз там нужно применить теорему 1 и избавиться от positive shifts. Значит, и если получится избавиться от них, то можно к полученной паре Лакса снова применить метод, и значит получится, и дальше дважды модифицированное уравнение вылезет, да. Значит, это проверено в некоторых примерах, работает, да.
Да, Максим выглядит доволен. Другие вопросы или комментарии есть? Okay, so yeah, I have the following question. So look, I mean, when we have differential equation and we construct Darboux and Backlund transformations, so okay, the main aim is to use them in order to construct solutions starting from simple ones, construct more complicated. So the first question is if you have any examples of solutions which you constructed using Miura transformations.
Well, using Miura transformations, one can often construct Backlund transformations using. We have the initial equation. We construct a Miura transformation over it, and then suppose that and there is a well-known trick. We have the modified equation, and suppose that we have an automorphism of the modified equation. So suppose that, well, you understand what is you mean?
Yes, I understand.
Asymmetry of the well. Suppose that in the modified equation we can make some transformation which preserves the equation. Then we get a second Miura transformation from the same modified equation to the initial condition, to the initial equation. We're taking the composition of this automorphism and the initial Miura transformation. So as a result, we get two Miura transformations. So from the we get two Miura transformations from the same modified equation to the same initial equation, which gives a Backlund transformation for the initial equation. And as you know, using a Backlund transformation, one can obtain interesting solutions.
Okay, I understand. Thank you. And the second question is the following. So as I said, when we construct Darboux-Backlund transformations, the main aim is to construct new solutions. However, they can be used to, as you know, to discretize PDEs by taking two Darboux transformations, the consistency around the square, and the corresponding Backlund will be Backlund for symmetries for this discrete system. So the question is there any other use of Miura transformations except constructing solutions? Can they be used in any other sense except construct solutions or constructing Backlund from them? Do they have any other positive properties, good properties or something?
So you see, so as I explained, using Miura transformations, one can often construct Backlund.
Backlund, yes, that I understood. I mean,
but then, so we get the following situation: we have a differential difference equation and a family of Backlund transformations for it. And this often allows to discretize the differential difference equation and obtain a difference equation, as you understand, right?
Yes, I understand.
So if you have a differential difference equation and
okay, so I think I pretty much understand. So look, I mean, if you have a PD, you get the Darboux transformation anyway, you get a Backlund anyway, you discretize anyway, but you mean that you have systems that look like the a question that the Darboux satisfies, which is actually your Lax pair for differential difference equations that do not come from PDEs, and for them it makes sense to construct Miura, which will help you discretize exactly this differential difference.
Yes, right, right. So, it is known that Miura transformations can be used for discretization effectively similar to Darboux transformations.
I understand. Okay, so you answered my question. Okay, thank you very much. Any more questions or remarks? Okay, in which case, Sergey, thanks very much again, and thanks all the speakers. And okay, it's only a few of us left, but however, I would like to thank all of you for visiting Yaroslavl, and on behalf of all the organizers, and we would like to see you again, and we hope to see you again, and we hope that you come and give us seminars on more detailed, in more details of what you already said. And okay, that's it. So hope to see you next year, or earlier than that.
Thanks a lot. Thanks a lot to Satiris, who is the main organizer of the conference.
Thanks, Sergey. So actually, for those who are still online, all the videos of your talk which you missed, you will find them on YouTube on the same links which you followed to watch live stream. So the talks are automatically being recorded to the YouTube. Okay, so I'm closing the conference. Bye, everyone.